Tonight, step outside if you can, or simply close your eyes and imagine it. Above you, the sky is doing what it has always done. Stars hold their places with quiet patience. The moon, if it is present, lays its pale light across whatever surface it finds. And somewhere beyond the reach of city glow, beyond the thin, scattered clouds of an ordinary evening, the band of the Milky Way arches from one horizon to the other, like a river that forgot how to flow downward. It looks permanent, it looks ancient, it looks above all else like something that has always been there and always will be. And that feeling, that deep intuitive certainty that the stars are fixtures, that the sky is a ceiling painted once and left unchanged, is one of the most beautiful illusions the universe has ever offered us. Because there was a time when none of it existed. Not a single star, not one galaxy, not one wisp of organized light anywhere across the entirety of space. There was a moment stretching across hundreds of millions of years when the universe contained everything it needed to eventually become what we see tonight, and yet showed none of it. The ingredients were present, the architecture was missing, the potential was immeasurable. The result was complete and total darkness. No stars burned, no galaxies turned, no nebulae glowed in faint colors at the edges of telescope images. If you had somehow been present in that era, suspended in the middle of what would one day become a universe full of light, you would have seen nothing at all. In every direction, in every wavelength your eyes could reach, there would have been only an invisible sea of gas drifting through expanding space, guided by forces you could not see toward futures that had not yet arrived. That era has a name. Astronomers call it the Cosmic Dark Ages, and it is where our story begins tonight. Not with a bang, not with a flash, not with the dramatic ignition most of us imagine when we think about the birth of stars and galaxies. Our story begins with silence, with darkness, with a universe that was for a very long time magnificently and completely unlit. If you enjoy falling asleep to the kind of wonder that makes the ceiling feel less like a ceiling and more like a window, I would be so grateful if you gave this video a like and considered subscribing to the channel. It helps more people find their way here, to this quiet corner of the cosmos, where we take our time with the big questions. Now settle in. Find whatever position your body has been asking for. Let the weight of the day begin to release. The universe has been patient for 13 billion years. It can certainly wait a few moments while you get comfortable. Let us begin. To understand how galaxies were born, we cannot start with galaxies. We have to start earlier than that. Much earlier. We have to go back to a time before stars, before planets, before any organized structure of any kind, back to when the universe was young enough that the word young actually meant something, when everything that would ever exist was packed into conditions so extreme that none of it looked anything like what it would eventually become. Imagine trying to describe a forest by starting with soil chemistry, or trying to explain a city by beginning with geology. The visible result and the original conditions can look so different from one another that connecting them requires patience. The universe requires the same patience from us. In the very earliest moments after the Big Bang, space was not the cold, dark, mostly empty expanse we know today. It was a place of extraordinary density and temperature. Matter as we understand it, atoms, molecules, the kind of stuff you can hold or measure or name, did not yet exist in stable form. Everything was compressed into a hot, dense plasma, a soup of particles and radiation so energetic, so tightly packed, that even the simplest atoms could not hold themselves together. Whenever a proton and an electron tried to form a hydrogen atom, a high-energy photon would immediately knock the electron free again. Structure was impossible. Everything dissolved before it could begin. Light existed, but it could not travel. That is one of the stranger facts about the early universe, and it deserves a moment of quiet attention. There was light everywhere. The universe was in a very real sense made of light saturated with it, and yet nothing was visible. Because visibility requires light to travel from one place to another, and in the early universe, photons could not move more than a tiny distance before colliding with a free electron and scattering in a new direction. The cosmos was opaque, not dark exactly, but impossibly foggy, like trying to see through a wall made of light itself. This continued for a long time, 380,000 years to be specific. 380,000 years of a universe full of energy, full of particles, full of motion, and yet utterly unreadable to any observer who might have tried to look across it. Then something changed. The universe had been expanding since the beginning, and as it expanded, it cooled. This is not a mysterious process. It is the same principle that makes a pressurized aerosol can feel cold when you release gas from it. Expanding matter loses energy, and losing energy means losing heat. The universe expanding on its largest possible scale cooled continuously and inevitably, and at around 380,000 years after the Big Bang, the temperature dropped to a threshold that changed everything. It dropped low enough for electrons to finally remain attached to protons. Neutral atoms formed. Hydrogen atoms, the simplest possible combination of one proton and one electron, appeared across the cosmos in enormous numbers. Helium atoms followed. And because neutral atoms interact with light very differently than free electrons do, the universe's relationship with its own photons changed completely in a relatively short period of time. The fog lifted. Light, suddenly free to travel, streamed outward in every direction. For the first time in cosmic history, a photon could move from one place to another without immediately scattering. The universe became transparent. And in that moment, that extraordinary transition that astronomers call recombination, the cosmos released a flood of light that is still traveling today. We detect it with our instruments. We call it the cosmic microwave background. It reaches us from every direction simultaneously, a faint afterglow stretched by 13 billion years of cosmic expansion from visible light into microwave radiation, so gentle now that it sits just a few degrees above the coldest temperature anything can ever reach. It is the oldest light in the universe, the first light that was ever free to travel. And when scientists map it carefully, when they build satellites specifically designed to measure its temperature across the entire sky with extraordinary precision, they find something that looks at first like almost nothing at all. The cosmic microwave background is almost perfectly uniform. From one patch of sky to another, the temperature varies by only about 1 part in 100,000. If you printed a map of it and colored it according to temperature differences, the hottest and coldest regions would be separated by such a tiny margin that you would need to look very carefully to notice any variation at all. That near-perfect smoothness is one of the most important facts in all of cosmology, because hidden inside it in those tiny, almost imperceptible variations is the origin of every galaxy that has ever existed. Here is the thing about near-perfect uniformity. It is not the same as perfect uniformity. And in a universe governed by gravity, the difference between almost smooth and perfectly smooth is the difference between a cosmos full of galaxies and a cosmos full of nothing interesting at all. If the early universe had been perfectly uniform, if every region of space contained exactly the same amount of matter as every other region, then gravity would have had nothing to work with. Every pull from one direction would have been exactly balanced by an equal pull from another. Matter would have stayed evenly distributed forever, thinning out as the universe expanded, never collecting into anything, never crossing any threshold, never producing a star or a galaxy or a planet or a thought. But the universe was not perfectly uniform. It was almost perfectly uniform. And almost is where everything begins. Those tiny temperature variations in the cosmic microwave background are the visible record of something that happened even earlier, likely in the first tiny fraction of the first second after the Big Bang, during a period cosmologists call inflation. The leading theory proposes that the very young universe underwent an episode of extraordinarily rapid expansion, not the steady expansion we observe today, but an exponential stretching of space itself, lasting an almost incomprehensibly brief time and increasing the size of the universe by an almost incomprehensibly large factor. During that inflation, something remarkable happened. At the quantum scale, the scale of the very smallest things where the rules of physics become probabilistic and uncertain, space itself was not completely still. Quantum fields fluctuated. Tiny random variations in energy density jittered in and out of existence, as they always do at that scale, as they are doing right now inside the atoms of every object in this room. Under normal circumstances, those fluctuations are microscopic and fleeting. They exist and dissolve before they can leave any lasting impression on the larger world, but inflation stretched them. Whatever quantum fluctuations existed in that earliest moment were pulled outward by the rapid expansion of space until they covered distances measured not in subatomic scales, but in what would eventually become cosmic ones. Tiny random ripples became large-scale variations in density. The universe was imprinted with a pattern not designed, not intentional, but statistically inevitable, a pattern of regions that were very slightly denser than average and regions that were very slightly less dense than average. And gravity from that moment forward had something to work with. The regions that were slightly denser attracted slightly more matter than their surroundings. That extra matter increased their gravity. The increased gravity attracted still more matter. And so on, across hundreds of millions of years, with the patience that only physics can sustain. Slight advantages became meaningful ones. Meaningful advantages became dramatic ones. The universe had begun, in its quiet way, to learn how to gather. But there is a complication. There is always a complication. Ordinary matter, the kind made of protons and neutrons and electrons, the kind that eventually becomes gas and stars and planets, and people had a problem in the early universe. It was too closely connected to radiation. The photons filling the early cosmos exerted pressure on ordinary matter. They pushed it around. They prevented it from simply collapsing under gravity the way it otherwise might have. On certain scales, this radiation pressure actually caused matter to oscillate, to compress, and then rebound, and then compress again in waves that moved through the early universe like sound waves through air. These are called baryon acoustic oscillations, and the evidence of them is still imprinted in the large-scale distribution of galaxies across the universe today, a preferred scale in how galaxies cluster together, a faint echo of sound waves that moved through the cosmos when it was younger than 380,000 years old. Ancient acoustics frozen into the architecture of the present universe. But here is the point. Ordinary matter was being held back by its connection to radiation. It could not simply collapse wherever gravity suggested. It was delayed. Dark matter was not. This is one of the places where dark matter becomes not merely interesting but essential. Dark matter does not interact with light in the way ordinary matter does. Whatever it is, and we do not yet know precisely what it is, which is one of the most important open questions in all of physics, it does not absorb or emit or scatter photons in ways that affect it meaningfully. It does not feel radiation pressure. It is not pushed around by light. And so while ordinary matter was oscillating, resisting, waiting for the universe to cool enough for atoms to form, dark matter was already doing something else entirely. It was clustering, quietly, invisibly, without announcing itself. Dark matter was responding to those tiny primordial fluctuations and beginning to collect into structures. By the time the universe became transparent, by the time ordinary atoms formed, and the cosmic microwave background was released, dark matter had already spent hundreds of thousands of years building something. Not stars, not galaxies, something more fundamental than either. Frameworks, gravitational wells, invisible concentrations of mass scattered across space, varying in size from what would eventually host a single small galaxy to what would eventually anchor an entire cluster. These dark matter structures had no light of their own. They emitted nothing. They reflected nothing. If you had tried to photograph them, you would have found only darkness where they were most concentrated. But they were there, and they were waiting for the ordinary matter of the universe, the hydrogen and helium gas, now free to move after the long hot plasma era, to begin falling in. Picture a landscape that you cannot see, a landscape of hills and valleys, sculpted entirely from something invisible, felt only through its gravity. And now, Anya, picture a fog beginning to settle across that landscape, a thin, cool fog of hydrogen gas drifting outward through expanding space. The fog does not fall into the valleys immediately. The universe is still expanding. Expansion carries matter apart on the largest scales, and so there is a contest, as there has always been in cosmic history, between the outward motion of space itself and the inward pull of gravity at specific locations where density has risen above the background. In many places, expansion wins. The gas keeps thinning. The density stays too low for gravity to take decisive hold. But in the places where dark matter had already built the deepest gravitational wells, in the places where the original fluctuations were largest, where matter had been collecting the longest, where the invisible framework was most concentrated, gravity eventually overcomes. The gas slows. It curves. It begins to fall. And as it falls, something happens that will determine the entire future of everything that follows. The gas heats up. This is not mysterious. It is the same principle that makes a bicycle pump feel warm when you compress air inside it. Compressing gas raises its temperature. Gas falling into a gravitational well is gas being compressed, and compressed gas resists further compression through pressure. So here is the situation. Gravity is pulling gas inward. The gas heats up as it falls. The heated gas pushes outward against further collapse, and for a long time these two forces reach an uneasy balance. The gas sits in a hot, diffuse state inside the gravitational well of a dark matter halo, but not yet cold or dense enough to form stars. Something else is needed. Something needs to allow the gas to lose the heat it gained during its fall. If the gas can radiate away its energy, if it can cool, then gravity can compress it further and further and further still, until densities rise high enough that something extraordinary becomes possible. That something is called cooling. And in the early universe, the most important agent of cooling was humble, even by the standards of humble things. It was molecular hydrogen. Two hydrogen atoms bonded together. H2, not the exotic, powerful, dramatic ingredient you might expect to find at the origin of galaxies. Just a simple molecule capable of vibrating and rotating in ways that allow it to radiate energy efficiently under the right conditions. In the cold, dark halos of the early universe, molecular hydrogen formed in small quantities and began cooling the gas from within. It was enough. Under the right conditions in the deepest and densest regions of these early halos, the cooling finally allowed gravity to win completely. Clouds began to collapse. The first stellar nurseries were taking shape. The darkness had learned very slowly and very quietly how to begin making stars. We should pause here for a moment and simply sit with what has happened so far. From quantum fluctuations so small they existed at the edge of physical meaning, through hundreds of millions of years of invisible dark matter assembly, through the release of the oldest light in the universe, through the long silence of the cosmic dark ages, through the slow drift of hydrogen gas into invisible gravitational wells, through the patient work of molecular hydrogen cooling clouds from within. From all that accumulated patience and physical inevitability, the first stars were about to switch on. No human being will ever witness that moment directly. The light from those first stars has traveled so far, been so stretched by the expansion of space, that detecting individual stellar objects from that era remains beyond even our most powerful current instruments. But we can reason our way backward toward it. We can trace the physics. We can run simulations on the most powerful computers humans have built, setting the initial conditions to match the cosmic microwave background and watching virtual universes evolve under known physical laws. And when we do, we find something consistent. We find that the first stars appeared roughly 100 to 200 million years after the Big Bang, perhaps somewhat earlier in some regions, perhaps somewhat later in others. The universe, as it always does, allowed a range of outcomes rather than a single synchronized event. But the direction was inevitable. Given the ingredients, given the physics, given the time, darkness was always going to end. And the way it ended tells us nearly everything about how galaxies eventually came to be. Tonight we have traveled from the first moments of the universe to the very edge of cosmic dawn. We have watched the hot plasma cool. We have seen the fog of the early cosmos lift. We have found the tiny fluctuations from which all structure grew. We have followed dark matter as it built the invisible scaffolding that ordinary gas would later fall into. And we have arrived at the threshold, that long-awaited moment when the first clouds of hydrogen were finally dense and cold enough to collapse. The first stars were preparing to ignite, and when they did, they would change the universe permanently. But that is where the next part of our journey begins. For now, let the darkness be enough. Let the quiet of those ancient eras settle over you, the way darkness settles over a landscape before dawn. Everything that would ever be beautiful about the night sky was already there, hidden in the silence, waiting. The universe has always been better at waiting than we are. And so tonight perhaps we can practice. Somewhere in the darkness, in a region of space that had spent hundreds of millions of years, slowly gathering itself, a cloud of hydrogen gas crossed a threshold. There was no announcement, no visible signal traveled outward to mark the moment. The universe did not pause to acknowledge what was happening. It simply continued doing what it had always done, following its own laws with complete indifference to the significance of the results. But in the core of that collapsing cloud, density and temperature had been climbing for a long time. The gas had fallen inward. It had compressed. It had heated. Cooling had allowed it to contract further. More compression had raised the temperature still higher. And now, in the dense, central region of that ancient cloud, something was happening that had never happened before anywhere in the universe. Hydrogen nuclei were being forced together. At the temperatures and pressures now present in that collapsing core, temperatures measured in the tens of millions of degrees, pressures beyond any earthly analogy, protons moved fast enough and close enough together that the strong nuclear force could reach between them. Two protons collided. Then, another pair. A chain of nuclear reactions began. Hydrogen fused into helium, and in that fusion a small amount of mass converted directly into energy. Energy poured outward from the core. Pressure built against the continuing inward crush of gravity. The collapse stopped. A balance was struck. A star had turned on. The first star to ignite in the history of the universe shone into a darkness that had no prior experience of starlight. There were no other stars to compare it to, no galaxies to contextualize it, no planets nearby to cast shadows. Just this single point of nuclear fire burning inside a vast sea of hydrogen gas, surrounded by the invisible scaffolding of dark matter, embedded in an expanding universe that had spent its first 100 million years or more preparing for exactly this moment without knowing it. We do not know precisely where this first star formed. We cannot point to a location in the modern sky and say with certainty that is where it happened first. The universe is too large, too old, and too thoroughly mixed for any single origin point to be traced so cleanly across the intervening billions of years. But we know what that first star probably looked like. And the answer is surprising. It was nothing like the Sun. The Sun is a middle-aged, moderately sized star that formed from gas already enriched by several previous generations of stellar chemistry. It contains hydrogen, yes, but also helium, carbon, oxygen, nitrogen, iron, and dozens of other elements in smaller quantities. These heavier elements, heavier than hydrogen and helium, which astronomers collectively call metals regardless of whether they are metals in the everyday sense, influence how gas behaves, how it cools, how it fragments, and what kinds of stars it tends to form. The gas from which the first stars formed contained almost none of these elements. It was pristine. It was the raw output of the Big Bang itself, roughly 75% hydrogen, 25% helium, and trace amounts of lithium. Nothing else. No carbon, no oxygen, no iron, no dust. That chemical simplicity had profound consequences. In the modern universe, when a cloud of enriched gas collapses to form stars, the heavy elements it contains help it cool efficiently and fragment into many smaller pieces. This is why most star-forming regions today produce a wide variety of stars, small ones, medium ones, and occasional large ones, with most of the mass ending up in relatively modest stellar bodies. But in the early universe, cooling was harder. The primordial gas, lacking heavy elements, could not radiate energy as efficiently. It resisted fragmentation into small pieces. Instead, clouds collapsed into fewer, larger concentrations. The first stars were almost certainly massive. Some may have been tens of times the mass of the Sun. Some may have been hundreds of times more massive. A few theoretical models suggest individual stars exceeding 300 solar masses may have been possible under those early conditions. Stars of that size are not merely larger versions of familiar stars. They are different creatures entirely. They burn at extraordinary temperatures. Their surfaces blaze with ultraviolet light so intense that they ionize surrounding gas across enormous distances. They consume their fuel at a rate so prodigious that what would be a 10 billion year lifespan for a star like our Sun collapses for these giants into a few million years. 3 million years perhaps, 5 million, 10 at the very most for some. In cosmic terms, that is not a life, it is a moment. Picture the first of these stars from a distance. If you could somehow stand far enough away to see it clearly, which would require an entirely unreasonable set of physical assumptions, but bear with this for a moment, you would see something fierce and blue-white at its center, pour light into a universe that had forgotten what light looked like. Around it, a bubble of ionized gas would be expanding outward, heated and stripped of electrons by the ultraviolet flood. The previously neutral hydrogen surrounding the star would be glowing in the soft red of recombination as electrons briefly joined protons before being knocked free again by the relentless radiation. And beyond that glowing bubble in every direction, there would be darkness, an ocean of neutral hydrogen stretching to distances so vast that the star's light, for all its ferocity, would thin to nothing long before reaching the next region where matter was dense enough to eventually do the same thing. The first star was alone, in the way that very few things in the later universe would ever be alone, not separated from neighbors by a street or a city or a country or even a galaxy, separated from any other luminous object by distances that light itself would take millions of years to cross. And yet even that solitary star was already beginning to change the universe around it. The ultraviolet light it produced was doing something crucial. It was ionizing hydrogen, stripping electrons from atoms in an expanding sphere around the star, converting neutral gas back into plasma. This was a purely local effect. At first, one bubble around one star, dwarfed by the vastness of the surrounding darkness. But it was a beginning. A small bubble of reionization created by a single stellar source in what would eventually become a cosmic tide. Meanwhile, inside the star, the real transformation was underway. Nuclear fusion in a stellar core is not a single reaction. It is a cascade. Hydrogen fuses into helium. In more massive stars, helium eventually fuses into carbon, carbon into oxygen, oxygen into neon, then magnesium, then silicon, then sulfur. Each step requires higher temperatures and pressures than the last. Each step releases energy, though, with diminishing returns as elements grow heavier. Eventually, in stars massive enough, the cascade reaches iron. Iron is the endpoint. It is the most stable nucleus, the configuration of protons and neutrons that requires the most energy to rearrange in any direction. Fusing iron does not release energy, it requires energy. And so when a massive star's core fills with iron, the fusion that has been holding it up against gravity suddenly stops producing enough outward pressure to maintain the balance. What happens next is one of the most violent events the universe permits. The core collapses. In less than a second, the iron core of a massive star, a sphere, perhaps the size of Earth, containing more mass than the Sun, falls inward and compresses into something almost incomprehensibly dense. A sphere perhaps 20 kilometers across, containing more than a solar mass of matter. At those densities, even the atoms themselves cannot maintain their structure. Protons and electrons are forced together, producing neutrons. The core becomes, in an instant, a ball of neutrons so dense that a teaspoon of its material would weigh 1 billion tons on Earth's surface. And then it bounces. The infalling outer layers of the star, still rushing inward at a significant fraction of the speed of light, hit the rigid, newly formed neutron core and rebound. A shockwave explodes outward through the star. Within seconds, the shock tears through layers of carbon, oxygen, silicon, and sulfur that took millions of years to build. It heats them to temperatures at which new nuclear reactions flash through the material, synthesizing elements that the star's slower burning never produced. Nickel, cobalt, elements heavier than iron, forged in the brief fury of the explosion rather than the patient burning of a long stellar life. Then the shock reaches the surface, and the star tears itself apart. A supernova. The explosion of one of these early massive stars may have briefly outshone everything else in its part of the universe. Not that there was much else. The early cosmos was still mostly dark, but into that darkness a dying star cast light equivalent to billions of suns for weeks or months before fading, and as it faded, it left behind something more valuable than its light. The debris from a supernova does not disappear. It expands outward at thousands of kilometers per second, carrying with it everything that stars spent its short life building. Carbon atoms forged in the stellar core, oxygen, silicon, iron, the newly synthesized heavier elements from the explosion itself. All of it, every element heavier than helium that this star had ever produced, now racing outward into the surrounding gas. For the first time in cosmic history, the universe contained something other than hydrogen, helium, and lithium in meaningful quantities. The first supernova had just changed the rules. This is not a small thing. This is in a very real sense one of the most consequential events in the entire history of the universe. Because those heavy elements scattered into the surrounding gas by this one dying star would alter everything that came after. Gas containing heavier elements cools more efficiently. It fragments more readily. It can produce a wider range of stars, including the small, longer-lived ones that burn steadily for billions of years, rather than flashing and dying in millions. It can eventually produce the conditions under which rocky planets form. And rocky planets are where everything interesting in our particular corner of the story eventually happens. But we are still deep in the early universe. One supernova's contribution to universal chemistry is tiny. The gas between the first stars is still overwhelmingly hydrogen. The traces of heavier elements scattered by that first explosion will be diluted across enormous volumes of space. The transformation of the universe's chemistry from primordial simplicity to the rich complexity we know today will require not one generation of stars but many. Millions of years of stellar birth and death, repeated across billions of locations, each cycle enriching the gas a little more. We are witnessing the first note of a very long piece of music. Now, let us think about what the first supernova meant for the small structure of gas and dark matter in which it occurred. The explosion did not happen in empty space. It happened inside what was probably the first rough ancestor of a galaxy, a small, dense concentration of gas within a dark matter halo, perhaps containing only a few 100,000 solar masses of ordinary matter, already forming a handful of massive stars in addition to the one that just died. The supernova's shockwave reached that gas. And what happened next depended on the balance of forces in this small system. In some regions, the shockwave compressed nearby gas, triggering new star formation. The explosion of one star caused others to ignite a brief cascade of stellar birth, pushed along by a wave of compression. In other regions, the energy was too much. Gas was heated beyond the ability of the small halo's gravity to retain it. Whole clouds were blown outward, escaping the gravitational well entirely, carrying their enriched contents into the surrounding intergalactic space. This is a crucial point about the earliest proto-galaxies. They were small. Their gravitational wells were shallow compared with what would later exist. A single supernova, or a handful of them, could have a dramatic effect on the gas supply of an entire early system. Larger explosions in larger numbers could temporarily shut down star formation completely by removing or heating the gas needed to continue. Then, after the energy dissipated and the gas cooled and fell back inward, star formation might resume, and then more stars would die, and the cycle would repeat. The very first galaxies were not steady factories efficiently converting gas to stars. They were turbulent, intermittent, self-disrupting systems, surging and pausing, heating and cooling, expelling and recollecting. They were learning how to sustain themselves through a process of explosive trial and error over millions of years. There is another consequence of those first supernovae that deserves its own moment of attention. Some of the most massive early stars did not explode as ordinary supernovae. Stars above a certain mass threshold may have undergone what theoretical astrophysics calls a pair instability supernova, a special kind of explosion in which the conditions inside the stellar core cause the production of electron-positron pairs, robbing the core of the pressure it needs to resist gravity and triggering a catastrophic runaway collapse and explosion. In a pair instability supernova, the entire star can be disrupted. No neutron star, no black hole remnant, nothing left behind except expanding debris. Other very massive stars may have collapsed directly into black holes, collapsing so completely and so rapidly that little or nothing escaped. These collapses would have produced black holes with masses, perhaps dozens or hundreds of times that of the Sun. not the supermassive black holes that live at the centers of galaxies today, containing millions or billions of solar masses, but seeds, starting points. Under the right conditions, abundant gas, frequent mergers, the compressed environments of early galaxy centers, those seeds could grow. Accreting gas merging with other black holes feeding on the turbulent material of young proto-galaxies. Over millions and then billions of years, some of them would become the supermassive black holes we observe today at the centers of galaxies, including our own. But that is a story for later. For now, note simply that the deaths of the first stars were not merely endings. They were in almost every case the beginning of something else. New elements scattered into gas. New shock waves compressing fresh clouds. New black hole seeds embedded in young halos. New ultraviolet radiation ionizing surrounding hydrogen. The first stars were brief. Their consequences were not. As more stars formed and died across more halos, the combined effect of their radiation began to do something on a cosmic scale. Each massive early star produced a bubble of ionized hydrogen around itself. In the beginning, these bubbles were isolated, separated by vast stretches of still neutral gas. They had no connection to one another. A universe of dark, neutral hydrogen punctuated by small glowing spheres of ionized gas around individual stellar sources. But as more stars formed in more halos, the bubbles grew, and eventually neighboring bubbles began to meet. When two expanding regions of ionized gas touch, they merge into one larger region. That larger region ionizes more surrounding gas. More stars form nearby. More radiation pours outward. More neutral hydrogen is ionized. The process accelerates. This is the Epoch of Reionization, the gradual transformation of the universe's hydrogen from mostly neutral back into ionized plasma, not through the heat of the early cosmos this time, but through the radiation of the first stars and the first galaxies. It did not happen all at once. Different regions of the universe reionized at different times depending on when stars formed there and how dense the surrounding gas was. Some regions lit up early when the first halos crossed the threshold for star formation. Others remained dark longer, waiting for more mergers, more gas accumulation, more time. Think of it as dawn arriving across a very large landscape at different times. Not a single sunrise sweeping evenly from east to west, but 1,000 small fires igniting at different hours, each one illuminating its immediate surroundings, the light eventually joining and spreading until the darkness that had been universal was replaced patch by patch, bubble by bubble by a universe that glowed. The Epoch of Reionization is thought to have lasted from perhaps 200 million years after the Big Bang to somewhere around 1 billion years after, though the exact boundaries remain one of the active frontiers of observational astronomy. Instruments like the James Webb Space Telescope are helping push our observations closer to that era, detecting galaxies from when the universe was only a few 100 million years old, trying to understand how and when reionization unfolded across cosmic time. What we know is that by the time it was over, the universe had changed permanently. The neutral hydrogen that had filled intergalactic space for hundreds of millions of years was gone, replaced by a warm ionized medium that has persisted in broadly similar form until today. The cosmic dark ages were over. They would never return. But let us not move past that transition too quickly, because there is something in it worth sitting with. For hundreds of millions of years, the universe contained everything needed to eventually produce galaxies, stars, planets, and the long chain of consequences that leads to a species lying in the dark, wondering where all of it came from. All the matter was there. All the physics was in place. The dark matter halos were assembling. The gas was drifting inward. The conditions were slowly, incrementally approaching the threshold. And yet there was nothing to see. No light that a human eye transported there could have detected. No warmth from nearby stars. No glow from distant galaxies. Just darkness and hydrogen and the patient, invisible work of gravity. Then a star turned on, then another, each one a local rebellion against the surrounding dark. Each one brief by cosmic standards but transformative in its effects. Each one producing light that for the first time in that region of space could travel freely to wherever it was going rather than scattering immediately into opacity. and each one producing in its death the elements that every subsequent generation of stars, including the one that eventually became our sun, would need in order to become more than just burning hydrogen. The first stars were not permanent fixtures. They were more like a first draft, an attempt by the universe to figure out through physical law, rather than intention, how stellar life could work under the conditions then available. The draft was rough. The stars were extreme. They lived and died so fast that no planet could have formed around them. No chemistry could have found time to become complex. No biology was possible anywhere nearby. But they changed the material. They changed the gas. They began the chemical enrichment that would eventually, across many more generations, many more cycles of stellar birth and death, produce the conditions in which a rocky planet, 4.5 billion years old, could develop oceans then. Life then, a species capable of lying quietly in the dark and asking how any of it started. And there is something personal in that chain if you allow yourself to follow it. The oxygen in your lungs right now was not present in the early universe. It did not exist during the cosmic dark ages. It was not there when the first stars ignited. It was forged eventually in the cores of stars that came later, stars born from gas, enriched by the deaths of earlier generations, including perhaps those very first population 3 giants. The carbon in your cells has a similar history. So does the calcium in your bones, the iron in your blood, the phosphorus in the chemistry that carries your genetic information. Every heavy element in your body required a star to make it, and a stellar death to release it. The chain from the first supernovae to the atoms currently inside you is long and indirect, passing through multiple stellar generations, through gas clouds that collapsed and dispersed and collapsed again, through a solar nebula 4.5 billion years ago that gathered and flattened and produced, among other things, a small rocky world at just the right distance from a middle-aged star. You are not separate from the history of the early universe. You are made of it. That is not a metaphor. It is chemistry. Tonight we have watched the universe's first stars ignite in the silence of the cosmic dark ages. We have seen them burn with extraordinary fury for only a few million years, then tear themselves apart in explosions that scattered the first heavy elements across the surrounding gas. We have followed the slow spread of ionized bubbles as more stars formed in more halos, until the reionization of the universe proceeded from isolated fires to a spreading, merging dawn. The darkness of the first cosmic era was ending. In the halos now scattered across the cosmic web, something more durable was beginning to take shape. Not just individual stars igniting and dying, but systems, collections of gas and stars and dark matter that were beginning to organize themselves into something that would persist through mergers and feedback and inflow and the long patient accumulation of mass into the earliest true galaxies. The universe was learning how to build cities. That is where our next part of the journey takes us. For now, let this be enough. Let the image of those first stars burning alone in the ancient darkness settle gently behind your eyes. Let the thought of their brief lives and their lasting consequences drift with you as sleep approaches. They did not know what they were beginning, neither does most of what begins in silence. But the universe had a direction. Quietly, relentlessly, it was moving toward complexity, toward light, toward structure, toward something billions of years later, wondering about all of it from the surface of a small, warm world. Rest now. The story continues whether we are awake for it or not. There is a temptation when thinking about the first galaxies to imagine something like the images that appear in astronomy textbooks and on the walls of science museums. Grand spirals with sweeping luminous arms. Ellipticals glowing soft and golden in the dark. Clusters of these elegant systems arranged like jewels across deep field photographs taken by telescopes hovering above the atmosphere. That temptation is understandable. Those images are genuinely beautiful, and they are genuinely real. Real galaxies, real light, real physics, made visible. But they are not what the first galaxies looked like. The first galaxies were rough. They were compact and irregular and turbulent. They had no sweeping arms because the conditions for sweeping arms had not yet been established. They had no quiet elliptical glow because the long settling that produces such smoothness had not yet had time to occur. They were in the most honest description available construction sites, active, chaotic, constantly disturbed by inflow and explosion and collision and feedback systems in the process of becoming, rather than systems that had arrived. And yet they were extraordinary, because they were the first durable structures in the universe where gas and stars and dark matter had begun operating together as communities rather than isolated events. The first places where something more than a single stellar generation was possible. The first rough drafts of everything that would eventually become the Milky Way and Andromeda, and the hundreds of billions of other galaxies now scattered across observable space. Tonight we visit them, these early, imperfect, magnificent ancestors. To understand what the first proto-galaxies were like, we need to begin with the environment in which they formed. And that environment was defined more than anything else by one simple fact. Everything was closer together. The universe has been expanding since the Big Bang. Every year that passes, the average distance between unbound structures grows slightly larger, which means that the further back in time we look, the smaller the observable universe was, not in terms of its total extent, which may be infinite, but in terms of the distances between the structures within it. In the first billion years of cosmic history, the dark matter halos that would eventually host galaxies were packed into a smaller overall volume. They were closer to their neighbors. Collisions and mergers between halos were more frequent. Gas streams feeding individual halos were more active, arriving from shorter distances along denser filaments. The early universe was, compared with today, a crowded and dynamic place. Not crowded in the sense of a city street, the distances involved were still enormous by any human measure, but crowded in the sense that gravitational encounters between structures happened more often on shorter timescales with greater consequences. Into this environment, the first proto-galaxies emerged. They formed inside dark matter halos that had grown through the bottom-up assembly we discussed in earlier chapters. Small halos merging into larger halos drawing in gas from surrounding filaments, gas cooling in the densest central regions and fragmenting into stars. The cycle of stellar birth and supernova death, enriching the surrounding material, and new gas continuously arriving to replenish what had been used or expelled. The earliest of these systems were tiny by later standards. Some may have contained only a few million solar masses of stars, less than 1,000th of the Milky Way's current stellar mass. Others were somewhat larger, but all of them were small enough that the energy released by even a modest population of massive stars could have a dramatic effect on the entire system. This is one of the defining features of early proto-galaxies, and it shapes almost everything about how they behaved. Imagine a small dark matter halo, call it a few 100 million solar masses of invisible gravitational structure, with a reservoir of gas sitting at its center. Gravity has pulled that gas inward. Cooling has allowed it to condense. Star formation has begun. The first massive stars in this system are now burning, pouring ultraviolet radiation into the surrounding gas, ionizing the hydrogen nearby, heating the medium through which future generations of stars would form. A few million years pass. Those massive stars reach the end of their brief lives. They explode. The supernova shock waves expand outward through the gas of this small proto-galaxy. And here is where the shallowness of the gravitational well becomes decisive. In a small system, the escape velocity, the speed needed to leave the halo entirely, is relatively low. The shock waves from a few supernovae can accelerate gas to speeds that exceed that threshold. Gas leaves. Not all of it, not instantly, but a significant fraction of the gas that was available for future star formation gets expelled from the system in winds driven by stellar feedback. The proto-galaxy for a time loses its fuel supply. Star formation slows or stops. The system dims. This might sound like a failure. It is not. It is regulation. Because the expelled gas does not simply vanish. It expands outward into the surrounding intergalactic medium, enriching it with the heavy elements produced inside the stars that just died. It mixes with the gas in the cosmic filaments surrounding the halo, and over time some fraction of it cools, loses energy to radiation and begins falling back inward. Eventually fresh gas arrives at the center again, densities rise, cooling restarts, a new generation of star formation begins, more massive stars ignite, more supernovae follow, more gas is expelled, and the cycle repeats. This self-regulating pattern star formation consuming gas stellar feedback, expelling gas, expelled gas, eventually returning or being replaced, is one of the most important features of galaxy evolution. It prevents galaxies from converting all their gas into stars too quickly. It maintains a supply of raw material across cosmic time. It connects the internal chemistry of a galaxy to the larger cosmic environment surrounding it. And it was operating in rough and turbulent form in the very first proto-galaxies. The universe did not simply build galaxies and leave them alone. It built systems that continuously negotiated with themselves. Now let us talk about what these early systems actually look like in the visual sense. Because even though we cannot travel back in time to observe them directly, we have two powerful tools for understanding their appearance. The first is observation. Modern telescopes, especially the James Webb Space Telescope, which began returning science data in 2022, can observe galaxies so distant that their light has traveled more than 13 billion years to reach us. Because light takes time to travel, observing distant objects means observing them as they were in the past. The most distant confirmed galaxies detected by Webb existed when the universe was only a few 100 million years old. And what those ancient systems look like, even in the compressed, redshifted, partially resolved images our instruments produce, tells us something real about what early galaxy formation produced. The second tool is simulation. Using the initial conditions encoded in the cosmic microwave background, combined with known physical laws governing gravity, gas dynamics, star formation, and feedback, astrophysicists can run computational models of cosmic evolution. These simulations start from the smooth early universe and evolve it forward for billions of years, producing virtual galaxies that can be compared with observations. When simulations and observations agree, we gain confidence that we understand the underlying physics. When they disagree, we learn something new. Both tools tell a consistent story about early proto-galaxies. They were compact, much more compact than modern spirals of equivalent mass. A proto-galaxy that would eventually grow into something comparable to the Milky Way might in its earliest stages have occupied a volume many times smaller than the Milky Way occupies today. Stars were packed more tightly. Gas densities were higher. The pace of events, star formation, stellar death, chemical enrichment was faster. They were clumpy. Rather than distributing star formation smoothly across a disk or a bulge, early galaxies tended to form stars in discrete, bright knots, dense regions of gas collapse that lit up intensely, then faded as their fuel was consumed. A young proto-galaxy might have appeared as a handful of brilliant, irregular blobs rather than a smoothly glowing structure. And they were turbulent. The random motions of gas within early galaxies were much larger relative to the ordered rotation of the system than in modern spirals. Gas moved chaotically, driven by inflows from outside, by supernova explosions from within, by the gravitational disturbances of frequent encounters with neighboring structures. Order was present in embryonic form. It had not yet had billions of years to establish itself. There is a particular observation that illustrates this beautifully. When the Hubble Space Telescope produced its famous ultra-deep field, exposures of small patches of sky, taken over hundreds of hours, revealing thousands of galaxies at varying distances. The most distant galaxies visible in those images looked nothing like the nearby ones. They were smaller, irregularly shaped, clumpy, and often blue-blue, because they were forming massive young stars at prodigious rates. And young massive stars are intensely blue-white in color. Those distant blue, irregular blobs were not failed galaxies or abnormal ones. They were young ones. They were what galaxies look like when they are still in the process of becoming. Webb has extended this view even further, detecting systems from earlier cosmic epochs that appear even more compact and irregular. Some are so small and so bright with star formation that astronomers are still working to understand how they assembled so much stellar mass so quickly. They push against the boundaries of what our models predict, not by breaking the physics, but by showing us that the early universe may have been even more efficient at building galaxies than we had conservatively assumed. Science, confronted with surprising data, does what science does. It refines its assumptions and continues. Now let us follow one of these early proto-galaxies through a particularly important kind of event, a merger. Two small halos, each containing a proto-galaxy at various stages of development, approach one another through the cosmic web. Their dark matter halos are the first to begin interacting the extended invisible envelopes, reaching toward each other long before the luminous gas and stars at their centers are anywhere close to touching. As the halos draw nearer, tidal forces begin to distort them. Dark matter, which cannot radiate energy away through electromagnetic processes, responds to these forces by stretching and mixing. The halos begin to overlap. Stars within each system, widely separated by the vastness of space, even within a small galaxy, mostly pass by one another without direct collision. But the gravitational environment in which they move is rapidly changing. Orbits that were stable are now disturbed. Stars from each system begin to mix with stars from the other. The gas tells a different story. Gas clouds within the two systems do collide. Gas is collisional. It interacts electromagnetically, meaning clouds that run into each other compress heat and shock. Where two streams of gas meet at high speed, temperatures spike dramatically. Then, cooling processes work to bring those temperatures back down. And where hot gas cools rapidly in a compressed region, the conditions for star formation are met with particular efficiency. Mergers trigger star formation dramatically intensely in bursts. For a period during and after the merger, the combined system may form stars at a rate far higher than either progenitor managed independently. Brilliant blue clusters of massive young stars blaze across the disturbed gas. Supernova rates climb as those massive stars die in rapid succession. The system is simultaneously more productive and more chaotic than anything it was before. Astronomers see this in the modern universe. Interacting galaxies, pairs caught in the process of merging, often show elevated star formation rates and disturbed morphologies. The Antennae galaxies, a famous pair in the constellation Corvus, are producing stars at a remarkable rate, precisely because two spiral galaxies are in the process of combining. Long tidal tails of stars stretch outward from the collision zone. Bright knots of star formation blaze in the compressed gas between them. What we observe in nearby merging galaxies today is a quieter, slower echo of processes that were much more common in the early universe when structures were closer together and collisions more frequent. In the first billion years of cosmic history, a small proto-galaxy might have experienced several significant mergers, each one bringing new gas, new stars, new angular momentum, new chemical enrichment, each one temporarily disrupting whatever order the system had managed to establish, then allowing a new, larger, more massive system to emerge from the chaos. Growth by merger was not an occasional episode in early galaxy formation. It was the dominant mechanism. But mergers were not the only way proto-galaxies grew. There was another pathway, quieter and more continuous, that simulations suggest was equally, or perhaps even more important for many systems: cold gas streams. The cosmic web is not merely a static framework. It is a network of filaments along which gas continuously flows toward denser regions. In the early universe, when filaments were narrow, dense, and feeding into compact halos, simulations suggest that cold gas that had not been heated by shocks to high temperatures, could flow directly into the centers of forming galaxies along these filamentary channels. This is called cold mode accretion, and it is one of the more counterintuitive ideas in modern galaxy formation theory. The naive picture of galaxy growth imagines gas falling into a halo, being shock-heated to high temperatures, slowly cooling over millions of years and then settling into the galaxy center. That process certainly happens. But in certain conditions, particularly in the early universe, in halos below a certain mass threshold, gas can instead flow inward along cool, narrow streams without ever being heated to high temperatures. The result is a continuous, relatively gentle supply of cold, dense fuel, flowing directly to where star formation can use it most efficiently. No long waiting period for hot gas to cool, no violent shock-heating phase. Just a steady stream of raw material arriving at the galaxy center, ready to collapse into stars. This cold accretion mode helps explain why some early galaxies were able to sustain high star formation rates for extended periods, rather than exhausting their gas in one brief intense burst. They were being resupplied continuously. The cosmic web was their fuel line. Inside these growing proto-galaxies, another crucial process was underway, one that would eventually determine the shape and character of the galaxies that emerged from these turbulent beginnings. Angular momentum was accumulating. We discussed in earlier chapters how gas falling into a dark matter halo acquires a net rotation, a slight overall spin inherited from the asymmetric gravitational torques of surrounding structures. In the early proto-galaxy stage, that rotation was present but subdued. The gas was too turbulent, too disturbed by inflows and supernova and mergers for ordered rotation to dominate the system's dynamics. But as time passed, as the most violent early episodes of star formation and feedback began to regulate themselves, as the merger rate slowed slightly, as halos grew larger and encounters became less frequent, something began to emerge. Order. Not perfect order. Not the serene, majestic rotation of a mature spiral galaxy, but the beginning of it. Gas that survived feedback and continued orbiting the halo center, gradually settled into a flattened, rotating configuration. Stars that formed from that gas inherited its rotational motion. A disk thin by later standards, but a disk nonetheless began to take shape. This transition from the compact, clumpy, turbulent proto-galaxy to something beginning to resemble a structured rotating system was not a single event. It happened at different times in different systems depending on merger history, gas supply, feedback intensity, and halo mass. Some systems developed rotating components surprisingly early. Others remained irregular and turbulent for longer. The universe, as always, preferred a range of outcomes to a single schedule. But the direction was consistent. Given time, given gas, given gravity, structure emerges. Now let us turn to something that was also developing during this proto-galactic era quietly, and in the background, in the densest central regions of the most massive early halos. Something was eating. In the centers of some proto-galaxies where gas densities were highest and gravitational focusing was most extreme, the black hole seeds left behind by the deaths of early massive stars were beginning to grow. Gas falling toward these central concentrations of mass could not all be converted into stars. Some of it spiraled inward on trajectories that brought it too close to the central black hole to escape. It formed an accretion disk, a swirling, heated, compressed region of gas and dust, tightening inward toward the event horizon. As it spiraled in, it released energy. The efficiency with which accreting matter around a black hole releases energy is extraordinary, far higher than the efficiency of nuclear fusion in stellar cores. A small amount of mass falling toward a supermassive black hole can release enough energy to outshine an entire galaxy of stars. When accretion rates are high enough, the central engine becomes what we call an active galactic nucleus, a brilliantly luminous core powered not by stars, but by gravity and infalling matter. In the early universe, some proto-galaxies hosted these active nuclei when their central black holes were still relatively small by later standards. The energy they released could heat surrounding gas, drive powerful outflows, and begin to regulate star formation in the galaxy around them, even though the black hole itself occupied a volume incomparably smaller than the galaxy it was. Influencing, this is one of the most remarkable scale mismatches in all of astrophysics. A black hole containing perhaps 1 million solar masses sits at the center of a system containing hundreds of billions of solar masses of stars and gas. Its physical size is negligible compared with the galaxy surrounding it, and yet the energy it releases during active accretion can influence matter across distances thousands of times larger than itself. The central engine was learning its role, and that role would become increasingly important as galaxies grew larger and more massive in the billions of years to come. Let us step back now and look at the first billion years of cosmic history as a whole, because when you hold it at a sufficient distance, a pattern becomes visible that individual details can obscure. The universe began with almost nothing in terms of structure. Smooth, hot, uniform except for the faintest statistical whisper of density variations. Then it produced dark matter halos. Then gas flowed into those halos. Then the first stars ignited and died and enriched the surrounding gas. Then proto-galaxies formed small, turbulent, clumpy systems that were already negotiating with themselves through star formation and feedback. Then those proto-galaxies began merging with each other and growing through cold accretion from surrounding filaments and developing the first seeds of central black holes. From nothing structured to something structured, from smooth to complex, from dark to lit, the direction was always the same, and the mechanism was always the same. Gravity given time and the slight imperfections of the initial conditions always moved matter toward greater organization. Not perfect organization, not simple organization, but organization nonetheless. Structure building on structure. Complexity arising from the patient amplification of original imperfections. The first proto-galaxies were not the destination. They were the beginning of a much longer process. They were the rough drafts from which the universe would eventually produce spiral galaxies and elliptical galaxies and galaxy clusters and superclusters and the entire cosmic web of luminous structure that modern telescopes reveal to us. But they were also, in their own rough way, magnificent, because they were the first time in the history of the universe that something as enduring as a galaxy existed at all. Think about what it means for a system to persist. The early universe was full of events that were brief. The first stars burned for a few million years and then died. Supernova shockwaves expanded and then dissipated. Individual gas clouds collapsed and then fragmented. Even dark matter halos, while long-lived, were continuously merging into larger structures, losing their individual identities in the process. A galaxy is different. A galaxy once formed above a certain mass threshold is something that can survive for billions of years while continuing to evolve. It can lose gas and regain it. It can experience mergers and recover from them. It can form stars for billions of years, then slow down, then revive. It can be stripped and disturbed by neighbors and still retain a core identity. The first proto-galaxies were the universe's first attempt at building something that would last. Not every attempt succeeded. Small systems could be completely disrupted by feedback or absorbed into larger ones without leaving a recognizable descendant. Some early halos may have hosted brief episodes of star formation and then gone dark, becoming what astronomers call fossil galaxies, ancient, faint, almost starless structures orbiting larger hosts. But others persisted. They grew through accretion and merger. They developed internal structure. They enriched their gas and formed new stellar generations. They attracted satellites and consumed them. They built history layer by layer, merger by merger, generation by generation. And billions of years later, their descendants include every galaxy in the observable universe, including ours. There is something I want you to hold as sleep approaches. A thought that requires no mathematics to appreciate, no specialist knowledge to feel the weight of. The Milky Way galaxy. The structure you are physically inside right now, the gravitational community to which your body belongs, as surely as it belongs to Earth, did not begin as a grand spiral. It began as something like what we have been describing tonight: compact, turbulent, small by later standards, actively forming stars in a way that it no longer does with the same intensity. It merged with companions. It absorbed smaller systems. It was enriched by generation after generation of stars that formed, burned, and died inside it over billions of years. It settled gradually into the rotating disk we now call home, and it continues to evolve. It is still accreting gas, still forming stars at a modest rate, still interacting gravitationally with its satellites, still moving with the entire local group through the cosmic web. The galaxy is not finished. You are not living in a completed monument. You are living in a process. And the process began billions of years ago in a small, turbulent concentration of gas and dark matter that looked nothing like the graceful band of light overhead on a clear night. That band of light is what a rough beginning looks like after 12 billion years of patient becoming. Rest now. Let that thought accompany you into the dark. Everything around you, the air, the room, the earth beneath you, the sky above, is downstream of those first chaotic galaxy-forming epochs. You are what the universe eventually made from its rough early work. And it did not do badly. Look at enough galaxies and the universe begins to feel like it cannot make up its mind. Some galaxies spread their arms outward in graceful spirals the way water curls around a slow drain lit from within by the blue-white fire of young massive stars, tracing the arm's compressed edges. Others appear smooth and rounded, glowing with the warm amber light of older stellar populations, their shape suggesting nothing so much as enormous luminous eggs suspended in the dark. Still, others look like neither torn, asymmetric, clumpy, disturbed, as though caught in the middle of something they have not yet resolved. And then there are the truly strange ones, ring galaxies, where a circle of intense star formation surrounds a relatively empty center. Lenticular galaxies disc-shaped, but lacking the spiral arms that usually define disk systems. Polar ring galaxies, where one ring of stars orbits perpendicular to another. Systems so irregular, they resist any comfortable classification at all. Confronted with this variety, it is natural to ask whether the universe has a plan, whether there is some underlying logic to why one galaxy becomes a spiral and another becomes an elliptical, whether shape is destiny or whether it is biography. The answer, as with most honest answers in cosmology, is both and neither, and it depends. To understand why galaxies look different from one another, we have to begin with what all galaxies share at the moment of their formation. They all begin inside dark matter halos. They all receive gas from surrounding filaments. They all form stars, enrich their gas through stellar evolution, and experience some form of feedback. The starting ingredients are broadly the same. The physics governing those ingredients is universal. What differs is history, specifically three interlocking aspects of history that together determine a galaxy's character more reliably than any single factor alone. The first is angular momentum, how much rotational motion the system inherited from its formation environment. The second is merger history, how many significant collisions the galaxy experienced and when. The third is environment, where in the cosmic web the galaxy lives and what kinds of neighbors it has had across its lifetime. These three factors interact in complex ways. A galaxy with high angular momentum and a quiet merger history in an uncrowded environment will evolve very differently from one with low angular momentum and a violent collision history at the center of a rich cluster. And between those extremes lies an enormous range of intermediate cases, each producing a somewhat different outcome. That is why the universe looks the way it does when you catalog its galaxies. Not random, not identical, varied within a framework of physical law the way forests contain many different trees, precisely because the same underlying biology can produce many outcomes depending on soil, light, rainfall, and time. Let us begin with spiral galaxies, because they are the most visually iconic and because understanding them requires understanding what conditions favor their formation. A spiral galaxy is fundamentally a rotating system. Its defining feature, the disk within which the spiral arms are embedded, exists because angular momentum prevents gas from collapsing directly to the center. Gas with rotational motion cannot simply fall inward, it orbits, and as successive shells of infalling gas join the rotation, they settle into a flattened structure, a disk, because collisions between gas particles cancel out vertical motion while preserving orbital motion. Think of it this way. If you pour water into a bowl while spinning it gently, the water does not pile up in the center. It spreads outward and flattens into a rotating layer. Angular momentum is the organizing principle. The galaxy disk is the cosmic version of that flattened rotating layer built from gas falling into a spinning dark matter halo over billions of years. For a disk to survive and develop into a recognizable spiral, several conditions need to be met. The system needs sufficient angular momentum to begin with, which depends on how asymmetrically the halo grew through tidal torques and merger dynamics. It needs a supply of cold gas that continues arriving over long timescales, fueling star formation in the disk, rather than exhausting all available material in one early burst. And it needs to avoid catastrophic major mergers that would scramble the ordered rotation of the disk and throw stars onto random orbits. That last condition is particularly important. A disk is an ordered structure. Order in a gravitational system is fragile. It took a long time to build and can be destroyed relatively quickly by a sufficiently violent encounter. When two galaxies of comparable mass collide, what astronomers call a major merger, the gravitational disturbance is severe enough to disrupt both disks. Stars from both systems are thrown onto new trajectories that have no memory of the original ordered rotation. Gas is compressed and consumed in a burst of star formation, often removing much of the cold fuel that would otherwise sustain future disk growth. The remnant that emerges from the merger is typically a more spheroidal system round a smoother, with stars moving in many different directions rather than sharing a coherent orbital plane. That spheroidal remnant is one of the main pathways through which elliptical galaxies form. Elliptical galaxies are in some ways the most misunderstood galaxies in popular astronomy. They look simple, smooth, rounded, featureless. Their images lack the drama of spiral arms or the disturbed complexity of interacting systems. It is easy to glance at an elliptical galaxy and assume it is boring, a finished thing, a settled thing, a galaxy that has stopped doing anything interesting. That interpretation has things almost exactly backward. Many elliptical galaxies, particularly the large ones, have the most violent histories of any galaxies in the universe. They are smooth, precisely because they have been through so much. The drama of their past has been averaged out by repeated collisions and mergers that scrambled their internal structure into a configuration where no ordered motion dominates and no disk persists. A large elliptical galaxy at the center of a rich galaxy cluster may have grown to its current size through dozens or hundreds of mergers across cosmic time. Each merger brought new mass. Each merger also stirred the internal dynamics, adding stars in random orbits from the consumed companion to the already randomized orbits of the host. Over billions of years, repeated stirring produced a smooth, well-mixed, structurally uniform system. The smoothness is the record of the violence. The simplicity is the signature of a complicated past. There is also a chemical story embedded in elliptical galaxies. Because their most intense star formation typically occurred early when they were actively merging and consuming gas-rich companions in vigorous starbursts, they tend to contain older stellar populations than spirals of similar mass. Their stars formed mostly in the first few billion years of cosmic history, used up or expelled most of their cold gas in that early burst, and have been forming new stars only slowly or not at all since. This gives ellipticals a characteristic warm amber or yellowish color. The blue-white light of young massive stars is absent because young massive stars are mostly absent. What remains is the gentler light of longer-lived lower-mass stars, stars that formed billions of years ago and are still quietly burning today. Astronomers sometimes describe this as a galaxy being red and dead. The phrase has a certain bleakness to it, but the reality is more nuanced. Even a quiescent elliptical is still evolving, still aging its stellar population, still accreting occasional gas from satellites, still participating in the dynamics of its cluster environment, still experiencing the slow internal rearrangements of a gravitationally bound system. Dead implies stopped. Ellipticals have not stopped. They have slowed. Now, let us talk about what determines whether a galaxy's merger history is violent or relatively quiet. Because this is where environment enters the story in a fundamental way. The cosmic web is not uniform. It contains regions of very high density nodes where multiple filaments intersect, where dark matter and ordinary matter have accumulated over billions of years into galaxy groups and clusters. And it contains regions of lower density, quieter filaments, and the vast underpopulated voids between them. A galaxy forming at a dense node in what will eventually become a rich galaxy cluster is born into a crowded neighborhood. Its dark matter halo, formed early, grew quickly through rapid accretion and was surrounded by many other halos at various stages of development. Mergers were frequent from the beginning. The pace of interaction was high. Such a galaxy tends to grow rapidly in the early universe, consuming companions and accumulating mass through repeated mergers. Its star formation is intense but relatively brief because the gas is consumed or expelled quickly. Its disk is disrupted by the frequent collisions. It ends up in many cases as a large elliptical galaxy, living at the center of a cluster, massive, smooth, ancient in its stellar population, surrounded by the smaller systems that did not achieve the same dominance. A galaxy forming in a quieter region of the cosmic web, on a less dense filament away from major nodes, experiences a very different biography. Mergers happen but less frequently. The pace of interaction is lower. Gas can arrive more steadily over longer timescales without being immediately consumed in a starburst. Angular momentum has more time to establish ordered rotation before a major merger disrupts it. Such a galaxy tends to develop a disk. It forms stars gradually over billions of years rather than in one early intense episode. Its stellar population is mixed, some older stars from early formation, but also younger ones from more recent star formation in the disk. It retains cold gas that continues to fuel star formation into the present. This is broadly how spiral galaxies come to dominate in lower density environments and ellipticals in high density ones. The cosmic web sorts galaxies by their formation environment, and environment shapes the merger history that determines the final form. But the story is more complicated than a simple binary between spirals and ellipticals. The universe as we have established resists simple categories. Consider what happens to a spiral galaxy that falls into a rich cluster environment after already developing its disk. The galaxy arrives with ordered rotation, cold gas, ongoing star formation. Then it encounters the cluster. Galaxy clusters contain not only many galaxies but also enormous quantities of hot gas, a diffuse plasma pervading the space between the cluster members, heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster's assembly. This hot intra-cluster medium exerts pressure on infalling galaxies. As the spiral moves through the cluster, the ram pressure of the hot gas it is moving through can strip cold gas from its disk. In a process astronomers call ram pressure stripping, the effect can be dramatic. Cold gas, the fuel for star formation, is removed from the galaxy's disk as though a wind were blowing it away. Star formation declines. The disk, no longer receiving the cold gas inflow that sustained it, gradually exhausts its remaining supply. The spiral begins to fade. Its arms become less prominent as fewer young blue stars light them up. Its color shifts from the blue-white of active star formation toward the redder tones of aging stellar populations. What remains is sometimes called a lenticular galaxy, a disk system that has lost its spiral arms and its cold gas supply, retaining the disk shape but with the star-forming activity of an elliptical. Lenticulars are common in cluster environments. They are, in many cases, spirals that the cluster transformed. So cluster environments not only produce ellipticals through major mergers, they also produce lenticulars by stripping spirals of their gas. The cluster is a transformer of galaxy types, converting the variety of infalling field galaxies into the more homogeneous populations typically found in cluster cores. There is also the matter of what happens at the very centers of massive galaxies across cosmic time. Because the central black holes that began as small seeds in early proto-galaxies did not simply sit quietly through all of this activity. They grew. And as they grew, their influence on the galaxies around them became increasingly significant. Consider a massive galaxy, perhaps a future giant elliptical, in the process of undergoing a major merger with another gas-rich system. The merger funnels enormous quantities of gas toward the centers of both galaxies. Some of this gas forms stars in a starburst, but some of it reaches the central black holes and begins accreting. The black holes, now feeding, actively produce powerful radiation and outflows. Energy released by infalling matter around a supermassive black hole through jets, winds, and radiation pressure can heat the surrounding gas, drive it outward, and suppress further star formation across the entire galaxy. This is what astronomers call AGN feedback, feedback from an active galactic nucleus. It is one of the primary mechanisms by which massive galaxies are thought to have quenched their star formation in the early universe. The galaxy grew rapidly through mergers and starbursts. The central black hole grew alongside the galaxy, fed by the same mergers. Eventually, the black hole became massive enough that its active phases could heat and expel gas faster than it could be replenished. Star formation declined. Gas that might have formed future stellar generations was instead heated to temperatures at which cooling became extremely slow. The galaxy transitioned from blue and actively star-forming to red and relatively quiescent. The black hole did not merely sit at the center of the galaxy. It helped determine when the galaxy's most productive era would end. That is one of the deeper reasons why the most massive galaxies in the universe tend to be the oldest in terms of their stellar populations, not because they formed first in an absolute sense, but because their rapid growth through mergers fed both their stars and their central engines, and those central engines eventually imposed a limit on continued growth. Massive galaxies consumed their own fuel supply and turned off their own star formation through the very process of becoming massive. Small galaxies with smaller black holes and shallower gravitational wells were less affected by this mechanism. They could continue forming stars more steadily over longer timescales, which is why some of the most actively star-forming galaxies in the modern universe are relatively small and low mass. Now, let us return to the spiral galaxy, specifically because there is one more feature of its structure that deserves attention, something that seems, on first encounter, almost paradoxical: the spiral arms themselves. Spiral arms are the most visually striking feature of spiral galaxies. Long curved regions of intense star formation and bright young stars winding outward from the galactic center in patterns that seem impossibly graceful for something made of gas and stellar explosions. And yet spiral arms present an immediate puzzle. If the galaxy is rotating, if stars and gas are orbiting the center at different speeds, at different radii in the way we discussed in earlier chapters, then any fixed pattern of stars should be wound up. The inner parts of the galaxy rotate faster than the outer parts. Given enough time, any arm made of specific fixed stars would be wound tighter and tighter, eventually disappearing into an indistinguishable blur. And yet the arms persist. Many spiral galaxies have maintained their arms for billions of years. The resolution to this puzzle is one of the most elegant ideas in galaxy physics. Spiral arms are not fixed collections of the same stars. They are patterns, density waves that move through the disk independently of the individual stars and gas clouds within it. Think of a traffic jam on a long circular highway. The car's individual stars are always moving. They enter the jam from behind, slow down while inside it, and then accelerate away from the front. The jam itself, the pattern of higher density, can remain approximately stationary or move at a different speed than the individual cars. The cars flow through the pattern. The pattern persists. Spiral arms work similarly. Gas and stars flow into and through regions of slightly higher density as they orbit the galactic center. As gas enters an arm, it is compressed by the higher density environment. That compression triggers star formation. Young, massive stars ignite and shine brilliantly, lighting up the arm from within. Those stars eventually die and disperse, but new ones form as fresh gas continues flowing into the arm behind them. The arm glows not because it contains the same stars at all times, but because it continuously produces new ones as material flows through it. The pattern is self-sustaining, driven by the dynamics of the rotating disk, rather than by any fixed assembly of matter. This is why spiral arms look so spectacular in images. They are regions of continuous star birth, lit by the blue-white fire of short-lived massive stars. They are cosmic assembly lines, illuminated by their own products. And beyond spirals and ellipticals, there is the vast population of irregular and dwarf galaxies, systems that do not fit neatly into either category, that exist in enormous numbers throughout the observable universe, that are in many ways the closest living relatives of the proto-galaxies we explored in the previous chapter. Irregular galaxies come in many varieties. Some are intrinsically disordered small systems whose modest gravity never organized a stable disk or settled population. Some are the remnants of larger galaxies disrupted by encounters with more massive neighbors. Some are galaxies in the process of merging, caught in a state of transition between one form and another. Dwarf galaxies are particularly important in the context of galaxy formation. They are the most numerous type of galaxy in the universe. The Milky Way alone is surrounded by dozens of them, the large and small Magellanic Clouds being the most prominent, visible to the naked eye from the southern hemisphere as detached patches of the Milky Way's light. Dwarf galaxies are in many cases the least evolved of all galaxy types. Small, with shallow gravitational wells and limited star formation histories, they retain something of the character of early proto-galaxies. Irregular, gas-rich, in some cases with stellar populations that span a wide range of age. Studying dwarf galaxies in detail gives astronomers a partial window into what the building blocks of larger galaxies looked like before they merged into their current descendants. And those mergers continue. The Milky Way is in the process of absorbing the Sagittarius dwarf spheroidal galaxy right now. The Large Magellanic Cloud will likely be absorbed in the future. Each of these events adds mass, angular momentum, and chemical complexity to the Milky Way, while removing one more small galaxy from the local population. The universe is still building. The merger rate has slowed dramatically since the peak of galaxy formation billions of years ago. But it has not stopped. Step back far enough from this diversity of forms, spirals, ellipticals, lenticulars, irregulars, dwarfs, giants, and something becomes clear that individual categories can obscure. Every galaxy type is a snapshot in time, not a permanent identity but a phase in an ongoing process. A spiral can become an elliptical through a major merger. An elliptical can acquire a new disk if it accretes enough cold gas. A dwarf can be absorbed into a giant. A giant can grow by consuming dwarfs. No form is final. This is one of the most important realizations in modern galaxy evolution. Galaxies are not species that remain what they are across cosmic time. They are processes, physical systems undergoing continuous change shaped by their environments and histories, capable of fundamental transformation given sufficient time and the right encounters. What we observe when we survey the universe's galaxies is not a catalogue of permanent types. It is a series of snapshots taken at one moment in the ongoing evolution of systems that have been changing for billions of years and will continue changing for billions more. The diversity of galaxy morphology is not the universe presenting us with its finished inventory. It is the universe showing us its work in progress at the particular moment in cosmic history, when humans happen to develop the instruments to look. And there is something quietly reassuring in that if you allow yourself to feel it. We live in a universe that never finished deciding what to make of itself, that continues exploring its own possibilities through the dynamics of gravity and gas and time, that builds grand spirals and then disrupts them, builds ellipticals from their ruins, builds new structures from the debris of old ones. That keeps finding new arrangements within the same physical laws, the same initial conditions, the same fundamental ingredients. The diversity of galaxies is the universe's creativity expressed through physics. No artist required, no intention necessary. Only matter and motion and the patient consequences of a few elegant equations operating across distances and timescales so large that their products can spend billions of years simply becoming what they are. We live inside one of those products. On a rocky planet orbiting an ordinary star in the outer disk of a barred spiral galaxy that formed in its rough early form from the same physical processes that produced every other galaxy in the observable universe. Our home is not special in kind. It is special in the particular way that every galaxy is special as one unique outcome of a process capable of producing an almost infinite variety of outcomes. And tonight, somewhere above the ceiling of this room, that galaxy is still turning, quietly, patiently, without needing to be watched to continue. Rest now. The turning will go on without us. It always has. There is a map of the universe that most people have never seen. Not because it is hidden or classified or too technically complex to reproduce, but because the scales involved are so far beyond ordinary experience that the map itself feels more like philosophy than cartography. If you could somehow step outside the observable universe and look back at it, an impossible thought experiment, but a useful one, you would not see galaxies scattered randomly like dust on a dark surface. You would not see uniform brightness distributed evenly in all directions. You would see something that looks more than anything else, like a structure, like a web, like the remnant of an enormous and ancient network, built from something invisible, traced in something luminous. Filaments of galaxies stretching across hundreds of millions of light years, connecting at nodes where clusters sit like bright knots in a net. Between those filaments, vast regions of relative emptiness, not true vacuums, but spaces where galaxy density drops dramatically, where matter thinned out as the denser regions around them drew material inward over billions of years. And threading through everything, the underlying dark matter scaffold that organized ordinary matter into this pattern in the first place. This is the cosmic web, and understanding it is essential to understanding not only where galaxies came from, but where we came from, because the Milky Way is not floating in empty space independent of everything around it. It is embedded in this web. It is a product of this web. Its formation, its growth, its current character, all of it was shaped by the particular region of the cosmic web in which it assembled. Tonight, we pull back to the largest scale the universe offers, and then we come home. The cosmic web did not appear suddenly. It grew from the same primordial fluctuations we have been following since the beginning of this journey. Those tiny density variations in the early universe were not distributed randomly. They had a statistical structure, a specific pattern of amplitudes and scales imprinted by the physics of inflation and the subsequent acoustic oscillations of the early plasma. When gravity began amplifying those fluctuations, it did not do so uniformly in all directions from every point. It amplified the existing pattern. Regions that were slightly overdense on large scales became the sites of filaments and cluster nodes. Regions that were slightly underdense became the seeds of voids. The web that exists today is, in a profound sense, the grown-up version of the quantum fluctuations that existed in the first fraction of the first second after the Big Bang. That connection between the finest scale quantum physics of the earliest moment and the largest visible structures in the present universe is one of the most extraordinary threads running through all of cosmology. The universe stretched its smallest uncertainties into its largest patterns. Quantum became cosmic, random became structured. The process by which this happened is sometimes called gravitational instability. Overdense regions attract matter from their surroundings, becoming denser. Underdense regions lose matter to their surroundings, becoming emptier. The contrast between dense and sparse regions grows over time. What begins as a nearly uniform distribution evolves through billions of years of gravitational interaction into the dramatically structured cosmic web. But the web is not simply a collection of randomly placed overdensities. It has geometry. Sheets of matter form where two underdense regions meet. Filaments form where three or more underdense regions converge on a common boundary. Nodes, the densest, most massive structures, the future sites of galaxy clusters, form where multiple filaments intersect. This geometry is not imposed from outside. It emerges naturally from the physics of gravitational collapse in 3 dimensions. Matter tends to collapse first along one axis, forming sheets, then along a second axis, forming filaments, then along the third, forming the compact nodes we call galaxy clusters. The sequence produces the web-like appearance we observe. Galaxy clusters are the most massive gravitationally bound structures in the universe. A large cluster can contain hundreds or thousands of galaxies, along with enormous quantities of hot intracluster gas and dark matter, a total mass that can exceed 1,000 trillion solar masses. They sit at the nodes of the cosmic web like cities at the intersection of highways, drawing material from the surrounding filaments that feed into them. And they continue growing. Unlike galaxies in isolated environments, which may reach a relatively stable configuration and evolve quietly, clusters at cosmic web nodes are still actively accreting. Galaxies fall in along filaments. Smaller groups merge with the main cluster. The intracluster gas deepens. The total mass increases. The Virgo cluster, the nearest large galaxy cluster to our own local group, sits roughly 53 million light-years away. It contains more than 1,000 confirmed galaxies dominated by several giant ellipticals at its core, including Messier 87, the galaxy whose central black hole was imaged by the Event Horizon Telescope collaboration and became one of the most reproduced photographs in the history of science. An image not of a black hole itself, which cannot be directly seen, but of the shadow it casts in the glowing gas around it, a silhouette of gravity so extreme that light itself cannot escape. The Virgo cluster exerts a gravitational influence that reaches well beyond its visible boundaries. The local group, the small association of galaxies that includes the Milky Way, Andromeda, and several dozen smaller companions, is falling toward it slowly. Not fast enough for a merger on any near-term cosmic timescale, but drawn nonetheless. We live on the outskirts of a gravitational watershed that drains toward Virgo across tens of millions of light years. The local group itself is a modest structure by cosmic standards. It spans roughly 10 million light years, contains perhaps 80 or more member galaxies, most of them small dwarf systems, and is dominated by two large spirals, the Milky Way and the Andromeda Galaxy. These two galaxies are approaching each other, not quickly on human timescales. The Andromeda Galaxy is roughly 2.5 million light-years away, and the closing velocity between the two systems is approximately 110 kilometers per second fast, by ordinary standards imperceptibly slow, given the distance involved. The merger, when it eventually occurs, is expected to begin in roughly 4 to 5 billion years. That collision will transform both galaxies. Their disks will be disrupted, gas will be compressed and consumed in starbursts, stars will be thrown onto new orbits. The central black holes of both galaxies will eventually sink toward each other through dynamical friction and merge, producing gravitational waves detectable across enormous distances. The remnant will likely be a large elliptical galaxy, a quiet, smooth, reddening system settling into the long final phase of its stellar evolution. Our descendants, if any exist by then, will look up at a sky that bears no resemblance to the one above us tonight. The Milky Way band will be gone. The Andromeda Galaxy, currently visible as a faint smudge in the constellation Perseus, on dark nights will no longer exist as a separate object. The familiar constellations, already changing slowly, as the stars within them move through space, will be unrecognizable. But that future is billions of years away. Tonight, both galaxies are still themselves. Let us focus now on our own, the Milky Way. Standing outside on a clear, moonless night away from artificial light, you can see it. A band of faint, diffuse brightness stretching across the sky, from horizon to horizon, slightly irregular, slightly mottled, interrupted here and there by dark patches where dust clouds absorb the light of stars behind them. It looks ancient. It looks settled. It looks like something that has been there forever and will remain forever. None of that is true. The Milky Way is approximately 13 billion years old, but it was not always the galaxy it is today. It assembled gradually from smaller components through a process of hierarchical growth that mirrors the broader story of galaxy formation we have been following throughout this journey. Its history is written not only in its current structure, but in the ancient stars still orbiting within it, each one carrying chemical memories of the environment in which it formed. The oldest stars in the Milky Way are found primarily in the galactic halo, the roughly spherical region surrounding the disk, extending outward to distances of perhaps 300,000 light-years or more. These halo stars are ancient. Some formed more than 12 billion years ago in the first billion years of cosmic history, when the proto-galactic fragments that would eventually merge into the Milky Way were first establishing themselves inside dark matter, halos. These stars are identifiable by their chemistry. They contain very few heavy elements, very little iron, carbon, or oxygen relative to hydrogen. Astronomers measure this with a quantity called metallicity, which reflects how enriched a star's birth gas was by previous stellar generations. Low metallicity means old. The star formed from gas that had not yet been processed through many cycles of stellar birth and death. It is a record of an early universe, still chemically simple. Some of the most ancient Milky Way stars discovered have metallicities so low that they may have formed from gas, enriched by only a handful of previous supernovae, perhaps even just one. They are in a sense the grandchildren of the first stars, carrying in their elemental composition the signature of one or two stellar generations before them. The story of how the Milky Way assembled from these ancient beginnings is still being reconstructed in detail. It is one of the most active areas of research in modern astrophysics, driven particularly by the extraordinary data produced by the European Space Agency's Gaia mission. Gaia is a space telescope designed to measure the positions, distances, and velocities of approximately 1 billion stars in the Milky Way with unprecedented precision. By tracking how stars move their velocities in 3 dimensions, the shapes of their orbits around the galactic center, astronomers can identify groups of stars that share a common origin. Stars that were born together in a companion galaxy now absorbed into the Milky Way continue for billions of years after the merger to share orbital characteristics that distinguish them from stars born natively. These groups are called stellar streams, long arc-like assemblages of stars distributed across the halo, moving in coherent patterns that betray their shared ancient origin. They are the skeletal remains of galaxies the Milky Way consumed long ago, dispersed into individual stars, yes, but still moving together in ways that memory preserves. Gaia has revealed an extraordinary richness of these structures in the Milky Way's halo. Dozens of streams, each representing a past merger, each adding a chapter to the galaxy's assembly history. The most significant of these ancient mergers is known among astronomers as the Gaia Sausage Enceladus event. The name is ungainly. It reflects the independent discovery of the same event by different research groups using different terminology, but the event itself is one of the most important in the Milky Way's biography. Roughly 8 to 11 billion years ago, when the Milky Way was still in early formation, it experienced a major merger with a substantial dwarf galaxy. This companion was not a trivial system. It may have contained as much as several 100 million solar masses of stars, a significant fraction of the Milky Way's stellar mass at that time. The merger was energetic. It deposited stars deep into the inner halo. It heated and thickened the early galactic disk. It may have triggered a period of intense star formation in the proto-Milky Way. The stars from this absorbed galaxy are still with us. They orbit in the inner halo on elongated orbits stretched and looping trajectories that the Gaia spacecraft's data revealed by their distinctive velocity patterns. The ancient companion no longer exists as a separate object, but its stellar descendants remain billions of years later, tracing the memory of a collision that helped shape the galaxy we now call home. The Milky Way's disk, the flat rotating region where most of its stars live, where the Sun orbits where Earth and all its history is located, formed gradually from this turbulent beginning. As the most violent early mergers subsided, and gas continued settling into the growing halo, rotation organized the infalling material into a flattened structure. Star formation in the disk began in earnest, and has continued at varying rates for most of the galaxy's history. The disk itself has layers. The thick disk, a population of older stars with more eccentric orbits and higher vertical motions above and below the galactic plane, formed earlier during or shortly after the period of intense merging. These stars carry moderate but not negligible metallicities, suggesting they formed from gas that had been enriched by several stellar generations, but had not yet reached the chemical richness of later epochs. The thin disk formed later from progressively more enriched gas and contains both older and younger stellar populations. It is where most of the galaxy's ongoing star formation occurs. Giant molecular clouds, cold, dense regions where gravity has concentrated gas to the point of stellar ignition, populate the thin disk, particularly along the spiral arms. New stars are forming there right now in clouds of gas that also contain carbon, oxygen, silicon, and iron inherited from billions of years of preceding stellar chemistry. The Sun is a thin disk star. It formed approximately 4.5 billion years ago from a cloud of gas that already carried the chemical inheritance of multiple preceding stellar generations. Not a first-generation star, not an ancient halo relic, but a relatively recent addition to the Milky Way's stellar population, formed when the galaxy was already more than 8 billion years old. In cosmic terms, we arrived late. That lateness is worth dwelling on because it is easy to miss its significance. When the Sun formed, the Milky Way had already existed for the majority of its current age. The most intense period of the galaxy's star formation, when it was converting gas to stars, most rapidly when merger events were most frequent, when the proto-galactic turbulence of the early universe was still fresh, had long passed. The galaxy had already assembled most of its current stellar mass. Its disk had already settled into roughly its present configuration. Its central bar had already formed. The solar system did not emerge during the Milky Way's youth. It emerged in something closer to the galaxy's middle age. This timing may have mattered enormously for the possibility of life on Earth. The Sun formed from gas rich enough in heavy elements to produce rocky planets. Carbon, oxygen, silicon, iron, the ingredients of both Earth's structure and Earth's eventual biology, were present in the cloud that became the solar system because billions of years of stellar generations had enriched the galactic disk before the Sun was born. Had the Sun formed 1 billion years earlier, the gas would have been less enriched. Rocky planets might have been possible, but less easily. Had it formed much earlier still in the ancient halo, the metallicity would have been so low that rocky planet formation might have been severely impaired. The Milky Way had to age for billions of years before the right conditions existed for the solar system to form, before the chemistry was ready. We are not early arrivals in the universe. We are late ones, and that lateness is part of why we are here at all. Look outward from the solar system, which is located roughly 26,000 light-years from the galactic center, in a relatively calm stretch of the outer disk, and the Milky Way's structure becomes visible in its broad outlines, though never directly, because we are inside it. We cannot see the Milky Way the way we see other galaxies from outside, in a single image that reveals its full shape. We infer its structure from within piece by piece using radio telescopes that can see through the dust that blocks visible light, using the motions of stars and gas clouds to reconstruct the three-dimensional pattern of the spiral arms, using surveys of stellar populations to map the disk's thickness and extent. From these reconstructions, we know the Milky Way is a barred spiral galaxy. At its center, a bar of stars, roughly 27,000 light-years long, crosses the nuclear region, connecting the central bulge to the beginning of the spiral arms. The bar is not merely decorative. It funnels gas inward from the disk toward the center, feeding the central star-forming regions and the central black hole. It redistributes angular momentum within the disk. It influences the dynamics of the spiral arms that extend from its ends. 4 major spiral arms have been identified, though their exact number and configuration remain subjects of ongoing research. The Sun sits near a smaller arm, sometimes called the Orion arm or local arm, between the larger Perseus and Sagittarius arms. A modest address in an average neighborhood of a moderately sized galaxy, in a small group near the outskirts of a modest supercluster. Nothing about our location is exceptional, and that too is extraordinary, because nothing about our location needed to be exceptional for what eventually happened here to happen. The cosmic web gave us our location. The web's large-scale structure determined where the local group formed, which determined where the Milky Way assembled, which determined the environment in which the solar system eventually took shape. Our address in the universe is not random. It is the result of 13 billion years of gravitational dynamics operating from initial conditions set in the first fraction of a second of cosmic history. We live at a specific node in a specific filament of the cosmic web. That filament feeds into the Virgo supercluster, a vast assemblage of galaxy groups and clusters extending across roughly 100 million light-years. The local group sits on one of the outer tendrils of this supercluster, far from the densest central regions in a relatively quiet gravitational environment compared with the richly populated cluster cores. That quiet environment may have contributed to the Milky Way's survival as a spiral. Less frequent major mergers, less ram pressure stripping, less of the aggressive environmental processing that transforms spirals into lenticulars or ellipticals in dense cluster cores. The Milky Way's location in the cosmic web gave it the conditions in which a long-lived disk galaxy could persist, which gave the disk billions of years to enrich its gas, which gave the gas time to accumulate enough heavy elements, which made possible the formation of a solar system with rocky planets, which made possible oceans, which made possible the chemistry that eventually became biology, which made possible billions of years later a species lying in the dark thinking about all of it. The web is not background scenery. It is the context in which everything specific became possible. There is a particular thought that I find worth carrying into sleep on nights when the sky is clear enough to suggest what lies beyond it. Every point of light you can see from Earth is part of the Milky Way. Every individual star visible to the naked eye is a neighbor in our galactic home, within a few thousand light-years at most. The Milky Way band itself is the combined light of hundreds of billions of stars, too far and too numerous to resolve individually, their light blending into that soft luminous path across the sky. And beyond that band, beyond the entire visible extent of our galaxy, the universe continues for billions of light years in every direction, filled with hundreds of billions of other galaxies, each one a variation on the same fundamental theme we have been exploring tonight. Each one assembled from the same ingredients, each one shaped by the same forces, each one a unique product of its particular location in the cosmic web, its particular merger history, its particular gas supply and stellar generations. The Milky Way is one of them, not special in kind, particular in history. And within it, on a rocky world orbiting an ordinary star in a quiet stretch of the outer disk, something happened that may or may not have happened elsewhere in the universe. Something assembled itself from the available chemistry and developed over billions of years into a form that could ask where galaxies came from. That question came from inside a galaxy. The answer involves the entire universe. There is something in that circularity that I find deeply settling. We are made of the universe trying to understand itself. We are the cosmic web looking inward. We are what happens when matter and time and physical law are given long enough to interact. And tonight on this world, in this galaxy, in this particular corner of the web, that process is still continuing. Rest now. The web will hold. On the 18th of December, 2021, a rocket lifted off from a launch facility in French Guiana and carried into space the most complex scientific instrument humanity had ever built, the James Webb Space Telescope. Folded into its launch configuration like an origami structure of gold and silver and carbon fiber, packed into the nose cone of an Ariane 5 rocket, it rose through the atmosphere and separated from its launch vehicle and began the long journey to its operational position, a point in space roughly 1.5 million kilometers from Earth in the direction away from the Sun, where the gravitational influences of Earth and Sun balance in a way that allows a spacecraft to maintain a stable position while keeping its sun shield permanently oriented between itself and the heat and light that would otherwise overwhelm its extraordinarily sensitive instruments. The deployment sequence that followed was one of the most technically demanding operations ever attempted in space. Over the course of 2 weeks, the telescope unfolded itself, extending its sun shield, deploying its secondary mirror, opening its primary mirror segment by segment, until all 18 hexagonal gold-coated beryllium panels were locked into position, forming a collecting surface 6.5 meters across. Every step had to work. There were no astronauts available to fix problems. The telescope was too far from Earth for any repair mission. The 344 single points of failure that engineers had identified, any one of which could have ended the mission, had to be navigated successfully, one by one, across 2 weeks of careful, anxious operation. They all worked, and in the months that followed, as the telescope cooled to its operating temperature of -233 degrees Celsius, as its instruments were calibrated and its mirrors aligned with a precision measured in nanometers, Webb prepared to do what it was built to do, to look further back into the history of the universe than any instrument before it, to see the first light, to find the first galaxies. To understand why Webb is so different from its predecessors, including the Hubble Space Telescope, which transformed our picture of the universe over more than 3 decades of operation, we need to return to a concept we have encountered before: redshift. As the universe expands, the space through which light travels expands with it. Light waves are stretched by this expansion. The longer light travels through expanding space, the more its wavelength is stretched. Wavelength determines color. Stretched wavelength means shifted color, shifted toward the red end of the spectrum, and for sufficiently distant and ancient sources, shifted beyond visible red, entirely into infrared. The most distant galaxies, the ones that emitted their light when the universe was only a few 100 million years old, have had their light stretched so dramatically that what was originally ultraviolet or visible radiation arrives at Earth as near infrared or mid-infrared. Our eyes cannot detect infrared. Ordinary optical telescopes are not optimized for it. Hubble could see some infrared, but its sensitivity in those wavelengths was limited, and Earth's atmosphere absorbs significant portions of the infrared spectrum, which is partly why space-based observation matters. Webb was designed from the beginning to be an infrared observatory of extraordinary sensitivity, with a mirror nearly 3 times the diameter of Hubble's cooled to temperatures that minimize the telescope's own thermal emission, equipped with detectors of a sensitivity that surpasses anything previously placed in orbit. In practical terms, Webb can detect sources roughly 100 times fainter than Hubble could in certain infrared wavelengths. That improvement in sensitivity translates directly into the ability to observe more distant, more ancient, and more intrinsically faint objects than were previously accessible. For galaxy formation, this means Webb can see further back toward cosmic dawn than any previous instrument. It can observe galaxies that formed when the universe was only 3 or 4% of its current age. It can study their properties, their stellar masses, their star formation rates, their chemical compositions, their sizes and morphologies with a level of detail that was impossible before. What it has found in its first years of operation has been extraordinary, and in some cases surprising. The first surprise arrived quickly. Within months of beginning science operations, Webb began identifying candidate galaxies at distances corresponding to when the universe was only a few 100 million years old. Some of these early candidates, based on their observed brightness and colors, appeared to be surprisingly massive, containing more stellar mass than the models of galaxy formation that existed before Webb's launch had comfortably predicted for systems that early. When this was first announced, it generated significant attention in the popular science press. Headlines suggested that Webb had broken cosmology, that the standard model of the universe was in crisis, that everything we thought we knew about galaxy formation was wrong. This was, as is often the case with such headlines, considerably overstated. What Webb had actually done was push observations into a regime where our models had limited prior observational constraint. The standard cosmological framework, built on decades of observations, theoretical development, and computational simulation, remained robustly supported by an enormous body of evidence. But the specific details of how quickly and efficiently galaxies assembled stellar mass in the very first few 100 million years of cosmic history had been poorly constrained observationally, because no previous instrument could see that. Far with sufficient sensitivity, Webb was not breaking cosmology. It was testing the extrapolation of our models into previously unexplored territory. And it was finding in some cases that the early universe may have been more efficient at building luminous systems than the most conservative pre-Webb estimates had assumed. That is not a crisis. That is science doing exactly what science is supposed to do, extending its reach, confronting new data, refining its understanding. The process of moving from initial Webb detections to confirmed properties of early galaxies involves an important technical step that is worth understanding because it illustrates how careful modern astronomy must be. When Webb images a very distant galaxy, the initial identification is often based on photometry, measuring the brightness of the source in multiple wavelength bands and looking for the characteristic pattern of colors that a redshifted galaxy produces. A galaxy at very high redshift will appear in some infrared bands, but not in shorter wavelength bands, because the expansion of the universe has shifted its light entirely out of the shorter wavelength range. This produces a distinctive dropout signature that astronomers use to identify distant candidates, but photometric redshift estimates can be uncertain. The color pattern that identifies a very distant galaxy can sometimes be mimicked by other objects at lower redshifts. Dust-obscured galaxies, unusual stellar populations, and certain rare objects can produce similar photometric signatures. Confirmation requires spectroscopy. By spreading the galaxy's light into its component wavelengths and identifying specific emission or absorption lines at known wavelengths, astronomers can measure the redshift precisely and confirm both the distance and various physical properties of the system. Webb's spectroscopic capabilities are as revolutionary as its imaging capabilities. Its near-infrared spectrograph can simultaneously observe the spectra of hundreds of objects in a single pointing, and its other spectroscopic modes can analyze individual objects with extraordinary sensitivity. The spectroscopic confirmations that followed the initial photometric detections have solidified our understanding of what Webb is actually seeing in those early epochs. And what it is seeing is genuinely remarkable. Among the most significant early findings is the detection of heavy elements, oxygen, carbon, nitrogen, in galaxies that existed when the universe was less than 1 billion years old. In some cases, significantly less. This matters enormously for galaxy formation theory. Heavy elements require stars to produce them. Stars require gas to collapse into them. Gas collapse requires time and the right physical conditions. The presence of substantial heavy element enrichment in very young galaxies implies that star formation began early, proceeded rapidly, and had already cycled through at least 1 or 2 stellar generations by the time Webb is observing these systems. In some of the most distant confirmed spectroscopic detections, Webb has found galaxies already showing oxygen emission lines, a clear signature of enriched gas when the universe was only 600 or 700 million years old. That enrichment implies stellar generations that formed, lived, and died before that observation epoch, which pushes the onset of active star formation even further back, perhaps into the first 300 or 400 million years of cosmic history. The universe was chemically busy very early, earlier in some regions than models had predicted with confidence. This finding also has implications for the Epoch of Reionization, that gradual transformation of neutral hydrogen into ionized plasma by the radiation of early stars and galaxies that we discussed in previous chapters. If galaxies were forming and enriching their gas earlier than expected, they were also producing ionizing radiation earlier. The reionization timeline may need to be pushed back slightly from some previous estimates. Webb is not rewriting the story. It is sharpening its chronology. There is another category of Webb discovery that carries particular weight for our understanding of galaxy formation: the detection of surprisingly massive and seemingly well-structured galaxies at very high redshifts. Some of the galaxies Webb has confirmed at redshifts, corresponding to when the universe was only 500 to 800 million years old, appear not only massive but relatively organized. Some show evidence of rotating disk structures. Some appear more chemically mature than the simple proto-galactic blobs that earlier theoretical intuition might have suggested for systems that young. This is surprising not because it is impossible within our physical framework, but because it suggests that the settling of galaxies from turbulent, irregular systems into more organized structures can happen faster, in at least some cases, than was commonly assumed. The leading explanation involves the particular conditions of early galaxy formation. In regions where dark matter halos were unusually massive and gas inflow through cosmic web filaments was particularly efficient, star formation may have proceeded so rapidly and so intensely that the most massive systems grew to maturity very quickly. Not because the laws of physics were different, but because extreme local conditions produced extreme local outcomes. The universe's variance, its tendency to produce a wide range of outcomes within the same physical framework, depending on environment and initial conditions, operated in the early universe just as it does in the modern one. Some early regions simply ran faster than the average. This is consistent with what we understand about hierarchical structure formation. The densest nodes of the cosmic web assembled the earliest, most massive halos, which hosted the earliest, most rapidly evolving galaxies. The very systems that would eventually become the giant ellipticals at the centers of today's rich galaxy clusters were in the early universe the most advanced and most chemically mature systems available to observe. Webb is in some cases detecting those systems in their youth and finding them already impressive. Perhaps the most cosmologically dramatic of Webb's early findings involves black holes. Among the early high redshift conformations are several active galactic nuclei galaxies with luminous central engines powered by accreting supermassive black holes. Some of these systems exist at redshifts, where the universe was less than 1 billion years old. Their central black holes already contain masses of millions to billions of solar masses. Growing a black hole to such mass in less than 1 billion years is challenging. Even accreting at the theoretical maximum rate, the Eddington limit, where radiation pressure from infalling matter balances the gravitational pull drawing it in a black hole starting from a stellar mass seed, would need to accrete continuously and efficiently for a very long time to reach the masses observed. The existence of these early massive black holes therefore implies one or more of several possibilities. The seeds from which they grew were already massive, not stellar mass remnants of individual population 3 stars. but perhaps the products of direct collapse of giant gas clouds into massive black holes without passing through a normal Stellarphase. Or the early accretion rates exceeded the standard Eddington limit in episodes of super-Eddington accretion, where the physics of inflow differs from the standard picture in ways that allow faster growth. Or the seeds merged frequently in the dense early universe, combining their masses rapidly before individual growth became the dominant pathway. Or all of these things happened in different proportions in different systems. Webb is providing new constraints on these possibilities by detecting and characterizing early active black holes across a wider range of masses and host galaxy properties than was previously accessible. Each new spectroscopic confirmation adds a data point. Each data point constrains the models. Each constrained model brings our understanding of early black hole growth closer to the actual history of the early universe. There is something almost detective-like about this process. The existence of billion solar mass black holes less than 1 billion years after the Big Bang has been established. The investigation into how they got there is ongoing. Webb has also revealed something about galaxy morphology at high redshift that connects directly to what we discussed in the previous chapter. The variety of galaxy shapes in the early universe is greater than older, less sensitive instruments could reveal. Some early galaxies appear compact and irregular, exactly what bottom-up hierarchical formation predicts. Others appear surprisingly disk-like, suggesting that ordered rotation established itself earlier in some systems than was expected. Still, others show evidence of ongoing mergers. Multiple bright components in close proximity, disturbed morphologies, tidal features confirming that the merger-driven assembly process we understand from theory was indeed operating in the early universe. One particularly striking morphological category revealed by Webb is what some astronomers have informally called little red dots, compact, extremely red sources that appear in Webb images at high redshift in numbers that initially seemed larger than pre-Webb models predicted. Their nature is still being actively studied. Some appear to be dust-obscured galaxies with intense star formation. Others may be active galactic nuclei, accreting black holes whose emission is reddened by surrounding dust. Some may be a combination of both. Understanding this population fully will require more spectroscopic observations and continued theoretical work. But their existence illustrates one of Webb's most important contributions, not only confirming what theory predicted, but revealing populations of objects that were previously invisible, whose properties challenge and extend our model of early galaxy formation. This is how science advances at its frontier, not by confirming a complete and correct theory in every detail, but by finding the places where the theory's predictions diverge from observation and using those divergences to identify what the theory is missing or underestimating. There is something profoundly moving about what Webb is actually doing when you step back from the technical details and hold the larger picture. Light that left its source more than 13 billion years ago. Light that began its journey when the universe was a fraction of a percent of its current age, when the first galaxies were still in the turbulent early stages of formation, when the Milky Way did not yet exist in any recognizable form, has been traveling through expanding space ever since, through the Epoch of Reionization, through the peak of cosmic star formation, through the long subsequent billions of years during which galaxies matured, merged, quenched, and evolved, through the formation of the solar system, through the entire history of life on Earth, through all of recorded human history. And then it entered the atmosphere of the planet, where it happened to be heading past through the outer atmosphere and fell onto the cold, exquisitely sensitive detectors of a telescope that a species of clever, curious primates had launched into space less than 3 years earlier. And those primates looked at the signal and measured it and thought about what it meant, and began to understand something about what the universe was doing 13 billion years ago. That chain of events, ancient light, expanding space, a rocky world, an evolved species, a gold-coated mirror, a moment of comprehension, is not something the universe planned. It is not something any of its individual components intended. It is what happened when physical law operated long enough in the right sequence in a particular corner of the cosmic web. And it is extraordinary. Webb's observations are also helping answer a question that has nagged at galaxy formation theorists for decades. The question of why the galaxy population looks the way it does today. Specifically, why there are not far more large galaxies than we observe. If galaxies simply accumulated gas and formed stars at the maximum possible rate for their entire lifetimes, the most massive halos in the universe should have converted most of their gas into stars long ago. The universe should contain far more giant galaxies than it does. Something must have limited star formation in the most massive systems. We discussed AGN feedback in the previous chapter, the way central black holes during active accretion phases can heat and expel gas from the surrounding galaxy. Webb is now providing direct observational evidence of this process in action in the early universe. It is detecting galactic winds, outflows of gas driven by AGN activity in galaxies at redshifts, corresponding to when the universe was only a few billion years old. It is measuring the temperatures and velocities of these outflows. It is beginning to quantify how much gas they remove from galaxies and how this removal affects subsequent star formation. This observational evidence for AGN feedback at early cosmic times helps validate the theoretical picture that had been built largely from simulations and lower redshift observations. The mechanism that limits galaxy growth, the central black hole periodically disrupting its own gas supply, was apparently operating in the early universe, shaping the galaxy population we see today by preventing the most massive systems from growing even larger than they did. The feedback loop between galaxy and black hole, each feeding on and limiting the other, was established early, and its consequences persist in the galaxy morphologies and stellar population distributions we observe across the modern universe. One final Webb contribution deserves particular mention tonight because it connects most directly to the beginning of our journey. The search for evidence of the very first stellar populations, the population 3 stars we discussed in earlier chapters. We noted that detecting individual population 3 stars directly is likely beyond the reach of any current or planned instrument. They formed too early, lived too briefly, and are too far away. But Webb is searching for indirect evidence of their existence through several approaches. One approach involves studying the spectra of extremely metal-poor galaxies at high redshift systems whose gas has been enriched very little, suggesting that relatively few stellar generations have cycled through them. The chemical patterns of enrichment in these systems, the ratios of different elements relative to each other, can carry signatures of the explosive deaths of very massive early stars that differ from the patterns produced by later stellar population. Another approach involves searching for a specific spectral signature, a helium emission line at a wavelength produced under conditions associated with extremely hot stellar sources, hotter than any normal stellar population would produce, potentially indicative of the ionizing radiation from population 3 stars embedded in very early galaxies. These searches have not yet produced definitive detections, but they are establishing limits telling us that if population 3 stars exist in certain numbers in certain kinds of galaxies, their signatures should appear above a certain threshold. When nothing appears, that absence itself constrains the models. Science advances through absences as well as detections. The universe reveals itself through both what we find and what we do not. Webb is not finished. It will continue operating for at least a decade, accumulating observations across an ever-growing range of targets and programs. Future data releases will extend spectroscopic confirmations to even higher redshifts. Larger surveys will provide statistical samples of early galaxies large enough to test theoretical predictions with genuine statistical power. New modes of observation will probe dust, gas, kinematics, and chemical abundances in early systems with increasing precision. And almost certainly there will be surprises. The history of astronomy is largely a history of finding what was not expected. Every time humanity's observational reach has extended significantly with the invention of the telescope, with the development of photographic plates, with the construction of radio and infrared and X-ray observatories, with the launch of Hubble, new phenomena have appeared that were not in the theoretical inventory. Webb will almost certainly add to that list. Perhaps it already has in data still being analyzed. Perhaps the most significant discovery it will make has not yet been made. That uncertainty is not a weakness of science. It is its most honest and most exciting characteristic. The universe is under no obligation to have shown us everything yet. What Webb is giving us above all else is access to the earliest chapters of the story we have been following tonight. The story that began with quantum fluctuations and dark matter halos and primordial hydrogen clouds and the first stars igniting in the cosmic dark ages. The story that produced proto-galaxies from turbulence and diversity from mergers, and the cosmic web from gravity's patient amplification of ancient imperfections. We have been reasoning our way toward the first galaxies using physics and simulation, and the observations that previous instruments made possible. Webb is now allowing us to observe those first galaxies. Not perfectly, not completely, not without significant ongoing work to understand what we are seeing, but directly. Photons that originated in the epoch of galaxy formation have arrived at our detectors and are being studied by human minds. The universe sent these messages 13 billion years ago. We are reading them now. There is a particular kind of wonder in that fact that does not diminish with familiarity. Every time I consider it, the age of that light, the distance it traveled, the precision required to detect it, the understanding required to interpret it, it feels like something that should not quite be possible. And yet here we are. A species that evolved on a rocky world in the outer disk of a spiral galaxy in a quiet corner of the cosmic web, pointing our instruments at the sky and reading the ancient history of the universe in light so faint and so old that nothing, in ordinary human experience, provides an adequate comparison. Rest now as this chapter of our journey closes. The telescopes will continue their vigil through the night. The ancient light will continue arriving, and tomorrow somewhere in an astronomy archive or a university office or a research institute, someone will open a file of Webb data and find something that changes what we know. The discovery of the universe is an ongoing activity. It has never stopped. It will not stop while curious minds exist to pursue it. And that perhaps is the most hopeful fact in all of science. We began tonight with a sky, your sky. The one above whatever ceiling or roof or open air currently separates you from the dark. The one that looks permanent and ancient and settled as though it has always been exactly what it is and will remain so indefinitely. The one that on clear nights reveals to anyone patient enough to look the faint luminous band of the Milky Way, stretching from one horizon to the other. 100 billion stars, reduced by distance to a soft continuous glow. Ancient light arriving from distances that make the word distance feel inadequate. We asked a simple question at the beginning: how did all of that come to be? And the universe, as it always does when asked direct questions, responded with complexity. It offered not a single answer, but a sequence of them, each one leading to the next, each one revealing that the question was larger than it initially appeared. That the formation of galaxies was not an event, but an era. Not a mechanism, but a collaboration between forces operating across scales ranging from the quantum to the cosmic, across timescales ranging from the first fraction of a second to the present moment. We have traveled a long distance tonight. Not in space, though. We have visited regions of the universe separated by billions of light years. In time, we have followed the universe from its smooth, hot uniform beginning through the long, patient darkness of the cosmic dark ages, through the ignition of the first stars and their brief, violent lives, through the emergence of the first proto-galaxies from turbulence and inflow through the slow diversification of galaxy types from a common origin, through the web-like architecture that connects every galaxy to every other, through our own galaxy's assembly from ancient fragments, and through the reports arriving now from the most powerful observatory humanity has ever placed in space. That is the story of how galaxies were born from silence. And it is also, in the most literal chemical sense, the story of how you came to be here, to hear it. Let us hold the summary gently, because summaries can make things sound simpler than they are. The universe began nearly 14 billion years ago, in a state of extraordinary uniformity, disturbed only by quantum fluctuations, so small they would have seemed insignificant to any observer capable of measuring them. Those fluctuations were stretched to cosmic scales by inflation imprinting the universe with a pattern of density variations that gravity would spend billions of years amplifying into structure. Dark matter, invisible and interacting, only gravitationally assembled the first frameworks, halos of unseen mass, into which ordinary hydrogen and helium gas eventually fell. That gas heated as it compressed, cooled through molecular processes, and in the densest regions, crossed the threshold into star formation. The first stars were massive, brief, and transformative. They burned with extraordinary intensity for only a few million years, then tore themselves apart, scattering the first heavy elements into the surrounding medium and ionizing the hydrogen around them in expanding bubbles of light. Those bubbles spread and merged until the cosmic dark ages ended, not in a single sunrise, but in a gradual, patchy billion-year dawn, as the first proto-galaxies multiplied and brightened, and their combined radiation reionized the intergalactic hydrogen across the observable universe. The proto-galaxies themselves were rough and compact and turbulent, nothing like the elegant systems that eventually descended from them. They grew through mergers and through the continuous inflow of gas along cosmic web filaments. They regulated their own star formation through feedback stellar explosions and central black hole activity cycling between excess and suppression, maintaining a balance that prevented them from consuming their gas too quickly or too slowly. Over billions of years they settled, ordered rotation, organized some into disks that eventually developed spiral arms. Major mergers scrambled others into ellipticals. Environmental processes transformed still others into lenticulars or disrupted irregulars. The cosmic web sorted these outcomes by location spirals in quieter regions, ellipticals in busy cluster cores, producing the distribution of galaxy types we observe across the modern universe. And in one particular spiral galaxy, in a quiet stretch of its outer disk, a cloud of gas enriched by more than 8 billion years of preceding stellar chemistry collapsed into a star and a surrounding disk of material that eventually produced, among other things, a rocky world with liquid water, an ATAT, an atmosphere, and the chemistry that spent another 4 billion years becoming biology, then intelligence, then the particular form of curiosity that builds telescopes and points them at the oldest light in the universe and asks what it means. That is the summary. But summaries are maps, and maps are not the territory. The territory is richer and stranger and more beautiful than any map. There is a question that sometimes goes unasked in discussions of galaxy formation, not the scientific question of how galaxies formed, which we have spent this entire journey exploring, but the philosophical question of what it means that we can ask the question at all. Consider the chain of events required for this moment to exist. Quantum fluctuations in the first instant of the universe had to be of the right amplitude to eventually produce structure. Dark matter had to exist in sufficient quantities to build the gravitational scaffolding that ordinary matter needed. The first stars had to form and die and scatter heavy elements before any later chemistry was possible. Those elements had to accumulate through enough stellar generations in the right proportions to produce the conditions for rocky planets. A particular star, in a particular galaxy, in a particular corner of the cosmic web, had to form at the right time with the right composition in a stable enough environment for a planet at the right distance to develop and maintain liquid water. Life had to emerge from that chemistry and persist long enough for natural selection to produce, over billions of years, a nervous system complex enough to model the external world, ask abstract questions about it, and communicate those questions across time and space to other members of the same species. Every link in that chain was necessary. The absence of any one of them, the wrong amplitude of fluctuations, no dark matter, no heavy element, enrichment, a different stellar environment, a slightly different planetary orbit, any of countless contingencies, and this moment does not happen. And yet here it is. Here you are, in a room, in a body made of ancient stellar material, with a mind that evolved on a rocky world in a spiral galaxy that formed from the same physical processes that shaped every other galaxy in the observable universe, listening to a description of how the universe built the structure you are inside. That is not a small thing. It may be the most remarkable thing in the observable universe. We do not know if it has happened elsewhere. That question whether minds capable of asking about the cosmos exist in other galaxies or even elsewhere in our own remains genuinely open. The universe contains hundreds of billions of galaxies, each containing hundreds of billions of stars, many of those stars hosting planets. The sheer number of opportunities for the chain of events that produced us to repeat itself elsewhere is staggering. And yet we have no confirmed evidence of it happening anywhere other than here. Perhaps that is because the universe is very large, and communication across it is very slow, limited as it is to the speed of light. Perhaps other minds exist, and simply have not made themselves known to us in ways we can detect. Perhaps the chain of events required is so specific, so dependent on particular conditions occurring in the right sequence, that it is rarer than the number of galaxies suggests. We do not know. And the honest response to not knowing is neither to assume we are alone, nor to assume we are not. It is to remain curious, to keep looking, and to appreciate what is here while its presence is certain. What is certain is this: one galaxy out of hundreds of billions developed within itself the conditions for a species that could look outward and recognize the universe for what it is, could measure the temperature of the cosmic microwave background to 5 decimal places, could trace stellar streams in the Milky Way halo back to ancient mergers that occurred before the solar system existed, could build a telescope the size of a tennis court, fold it into a rocket, launch it to a gravitational balance point, 1.5 million kilometers from Earth, unfold it in the precise sequence required, cool it to near absolute zero, and use it to observe light that began its journey when the universe was 3% of its current age. That is what happened in one galaxy. In this galaxy, the one you are currently inside, it is enough to make the night sky feel less like scenery and more like family. There is a particular image I want to leave with you as sleep approaches, not a dramatic image, a quiet one. Imagine the universe in its first 100 million years, before the first stars, before any galaxy. The cosmic dark ages, in their full extent, an ocean of neutral hydrogen and dark matter, expanding, cooling, organizing itself invisibly through the patient accumulation of gravitational advantage. No light, no warmth from nearby stars, no glow in any direction, but embedded in that darkness in countless locations across the expanding cosmos, something is happening that the darkness does not reveal. Gas is falling inward, dark matter halos are deepening, clouds are contracting, densities are rising. The preconditions for ignition are assembling themselves slowly and without announcement in hundreds of thousands of places simultaneously. The darkness is full of becoming, and then in one location, and then another, a threshold is crossed. A core reaches the temperature and pressure required for nuclear fusion. A star turns on, one point of light in a universe of darkness. One small rebellion against the surrounding cold. One nuclear fire burning in the silence that has held since the beginning. It does not know what it is starting. It does not know that its ultraviolet radiation will ionize the hydrogen around it and begin a process that will eventually reionize the entire universe. It does not know that when it dies, it will scatter elements that no previous process has produced, and that those elements will make future chemistry richer, and that richer chemistry will make future stars more diverse, and that more diverse stars will produce the conditions for rocky planets, and that rocky planets will eventually develop oceans, and that oceans will develop life, and that life will eventually produce a form of curiosity that builds telescopes and points them at the oldest light in the universe, and finds in that ancient light the record of the fluctuations from which everything, including itself, descended. It is just a star, burning in the dark, following the laws of physics with complete indifference to the significance of the result. And yet, from that one point of light, everything that makes this moment possible begins its long, improbable, magnificent unfolding. We are the descendants of that first light, not metaphorically, chemically. The heavy elements scattered by the deaths of early stars became the raw material for later stellar generations. Those later generations enriched the gas further. Eventually, in one galaxy, in one cloud, on one particular day, 4.5 billion years ago, a star formed from that accumulated inheritance, and around it, from the leftover material of its formation, a family of planets assembled. And on the third of those planets in an ocean, something happened that we still do not fully understand. Chemistry crossed a threshold into biology. And biology, over billions of years and trillions of generations, became the kind of thing that lies in the dark and thinks about where galaxies came from. That journey from the first point of light to this moment, from quantum fluctuation to conscious reflection, is the longest story the universe has told. It spans nearly 14 billion years. It involves processes operating at every scale, from the subatomic to the cosmic. It passes through epochs that no observer witnessed and leaves its records in ancient light, in stellar chemistry, in the distribution of galaxies across the sky, in the cold glow of the cosmic microwave background, and in the atoms of every living thing on Earth. It is the story of how silence became sound, how darkness became light, how simple became complex, how matter became in at least one corner of the observable universe aware of itself. Tonight, the sky above you contains all of it. The stars of the Milky Way burning in a galaxy that assembled over 12 billion years from ancient collisions and mergers, and the patient enrichment of stellar generations. The faint smudge of Andromeda, a companion galaxy approaching across 2.5 million light-years, carrying its own long history of formation and evolution toward an eventual merger that will reshape both galaxies into something neither currently is. The invisible structure of the cosmic web, threading dark matter through intergalactic space, along filaments that connect every galaxy to every other in a network that spans the entire observable universe. And beyond all of that, beyond the reach of any unaided eye, beyond even the reach of most telescopes, the first galaxies, compact and turbulent and bright, with the fire of young massive stars. Existing when the universe was young enough that the word young still had a meaning it no longer quite has, sending their light outward in all directions, most of it traveling through billions of years of expanding space before being collected by a gold-coated mirror, orbiting the sun at a point chosen for its gravitational stability and converted into data that human beings are still learning to read. Those first galaxies are not distant from us in any meaningful emotional sense. They are our ancestors. The matter that formed in them, the heavy elements scattered by their stellar explosions, the gas that flowed outward from their boundaries and eventually settled into later structures, contributed across billions of years of mixing and recycling and stellar reprocessing to the cloud. That became the solar system. The chain of material inheritance connects us directly to those first luminous structures in the dark. We came from there, in the only sense that ultimately matters, the chemical, physical, causal sense. We are what those first galaxies eventually became. The universe began in silence, in smoothness, in a darkness so complete that even the concept of darkness had no contrast by which to be defined, because there was nothing else. And then very slowly, and then less slowly, and then with increasing momentum across billions of years, it learned to make light. It learned to gather matter into stars, to use those stars as forges for elements that had not previously existed, to scatter those elements through stellar death into the surrounding gas, to build from that enriched gas new generations of stars, more diverse and longer-lived than the first, to organize those stars into galaxies, and galaxies into groups, and groups into the vast web of structure that now fills the observable universe. And somewhere in that web, in one unremarkable spiral galaxy in the outer reaches of its disk, on a rocky world that formed from the accumulated inheritance of more than 8 billion years of cosmic chemistry, somewhere in all of that, something happened that the universe had perhaps never quite managed before. It became aware of itself. It began to ask where it came from. It built instruments to find the answer. It looked back through 13 billion years of expanding space and found in the ancient light arriving at its detectors the record of its own beginning. That is what you are part of, not a passive observer of a universe that happened elsewhere and long ago. A participant, a product, a present expression of a process that began with quantum fluctuations smaller than any currently measurable scale and has been unfolding without pause ever since. The silence that preceded the first stars was not empty. It was full of potential, full of the becoming that was already invisibly underway. The silence that surrounds you now is the same. Whatever comes next in your life, in this galaxy, in this universe, It is already being prepared in ways too subtle and too slow for any single moment to reveal. Rest now. Let the darkness be what it is, not an absence of something better, but the patient medium through which all light eventually travels. The first star ignited from silence. Something in you ignited from the same long chain of cause and consequence. Both of you are in your different ways the universe keeping its oldest promise to itself, that there will be light, that it will be worth the wait, that the darkness, however long it lasts, is always full of what comes next. Good night. Sleep well. The stars are still out there. They have been waiting for you to rest since long before either of you existed.